So this is going to be, okay, May-June 2021 paper. Okay, so we will actually go through this paper. I will keep the marking key at the side so that we can check directly. Okay, maybe the marking key is a bit small, okay, but from time to time, I will actually try to write down in the question paper itself. Yeah, so this is going to be May-June 2021. Okay, let's begin. So here, okay, the first question over here is, okay, they ask about the carbonates and hydroxides of group 2 elements. Okay, they show similar trends in thermal stability. It means that carbonates and hydroxide, okay, they have the same trend. Yeah, the trend, you should know that going down the group 2, yeah, going down group 2, the thermal stability increases. Okay, thermal stability increases. So suggest and explain the variation in the trend. So you just say group going down, okay, going down the group, okay, the group thermal stability, okay, increases, okay, increases for both hydroxides and carbonates, but here they say hydroxide. Yeah, so it's okay. So for both carbonates, okay, and hydroxide. So the reason, okay, the reason behind this is going to be because of the, okay, because of the what we call as ion polarization. In AS, we learn about what will happen to the thermal stability. So they, you just need to remember, okay, it's going to be you require more heat, okay, to break down lower group 2 elements, which is the carbonates and hydroxides. So now, okay, you should know that, okay, we need to tell the reason. The reason is something to do with the ion polarization. Yeah, when we say ion polarization, we are talking about cation. Yeah, so when you go down, okay, as the cation, okay, becomes bigger, okay, or we say the ionic radius, okay, going down, okay, going down the group 2 cation have more ionic radius, okay, or large ionic radius, okay, which decreases the ion polarization, or the polarizing power is going to be decreased. Yeah, so if you have, okay, which the ionic radius which is going to be less, then you are going to have more ion polarization, especially when you're talking about more charge. But in this case, we are talking about group 2. Yeah, the charge is constant. So if you have more ionic radius, then ion polarization will not happen. So ion polarization, what is ion polarization? It's the ability to distort, okay, the electron cloud of the anion. Yeah, so the anion electron cloud of, okay, hydroxides are not distorted, okay, are not distorted, okay, and the bond between oxygen and hydrogen are not weakened. Therefore, okay, more energy required to break the bond. So if you compare, okay, with the marking key, now I'm going to check the marking key. So you can see that, okay, let's see whether anything we missed. Yeah, so it they say thermal stability increases, okay, down the group. So that's going to be your 1 mark. And the ionic radius, okay, you see the ionic radius or size, okay, of M2 plus increases. So I just mentioned that the ionic radius, okay, which is going to, they have more, okay, so that is already part of the answer. Yeah, so more ionic radius, okay, the group 2 cations, okay, you can see over here, that's going to be 1 mark. Okay, and then less polarization, you can see, okay, the decreases the ion polarization. Okay, so the ion I specify over here, which is going to be anion, which is what they want over here also. Okay, the distortion of anion, less distortion. So I also mentioned that they are not distorted. Yeah, they are not distorted that much. Okay, and then I even give more points that required. Okay, that is going to give you the 3 marks. Okay, let's move on. Okay, so then B, okay, but before we move on, okay, since the B they mentioned about, okay, solubility, okay, I will also try to go through the solubility as well. Okay, if you look at the solubility, okay, in our syllabus, we look at the solubility of hydroxides, group 2 hydroxides, and we look at the solubility of group 2 sulfates. And everyone should know, okay, as you go down, the barium is going to be at the lower part of the periodic table group. So it's going to be barium sulfate is always going to be white precipitate. So you should know, okay, solubility of sulfate is going to be decreasing, yeah, going down the group. Okay, so solubility decreases. Okay, and when you look at the solubility of hydroxides, okay, the solubility of hydroxide is going to be the other way around. Yes, solubility is going to increase. Okay, so it increases down the group. Okay, it's the other way around compared to sulfate. So you need to know about that. Yeah, but okay, in your AS, that is the part that they ask you. They just want you to know about the solubility increases or solubility decreases down the group. But in your A2, you need to mention why. And in order to mention why, you need to know the formula. We will apply the formula, which is going to be let your soul go and hide. Okay, we forget. Okay, lattice energy, let your soul. So go and put the soul over there to the right. So it's going to be negative, and hide. So it's going to be hydration. So if you want to memorize lattice energy is hydration minus solution, or if you want to memorize hydration equals to lattice energy plus solution, I will leave it to you. Yeah, but do remember lattice energy and hydration, they are always going to be negative in value. And this negative value, okay, this lattice and hydration, they depend on, okay, the charge divided by radius. Okay, it is similar to charge density. Yeah, so we know that going down the group, yeah, group 2, the radius, okay, is going to actually increase, and we know generally the charge is the same. So we know the something divided by bigger number, okay, the value is going to become smaller. Yeah, or you can say it is going to become more positive. Yeah, if you want to look at it in form of negative, or you can say the value, yeah, the value decreases. Okay, up to you how you want to show. Okay, but do remember, okay, you need to remember that both lattice energy and hydration, they are going to decrease, but one of them will decrease more, dominant. Yeah, so the one that is dominant, if you want to remember, I ask you to remember shift like this, right? Like that. Yeah, if it is SHH, yeah, if you want to remember, yeah, which is going to be for sulfate. Okay, the one that is going to be dominant is going to be hydration. Hydration will decrease more, yeah, compared to lattice energy. If that happens, if you apply into this formula, okay, if your hydration decreases more, what you will notice is, because in the end, I want the enthalpy of solution. Enthalpy of solution is going to be hydration minus lattice energy. Lattice energy is always negative, yeah. So you are going to get something like a negative value plus a positive value over here. Okay, what will happen? Yeah, what will happen if your hydration decreases? Okay, if your hydration decreases, what happened? Okay, your solution, okay, enthalpy of solution, okay, you just need to remember solubility decreases, enthalpy of solution, if the enthalpy of solution is a small positive, or okay, if it is going to be negative value, then they are soluble. Okay, so if the solubility decreases, it means that, okay, your enthalpy of solution is going to become positive. Okay, it's going to become more positive. So what will happen, okay, when this decrease of hydration, okay, happens and decrease of lattice energy, if you apply those values here, okay, you no need to show, you just need to mention, okay, if you apply there, your enthalpy of solution, okay, is going to be, your enthalpy of solution is going to become more positive. Okay, so when your enthalpy of solution becomes more positive, okay, that is going to tell us that the solubility decreases. Okay, this is going to be opposite to your hydration for the solubility of hydroxide. Okay, the decrease of lattice energy is larger. If you remember SHH like that, yeah, sulfate hydration decrease more. So of course for hydroxide, okay, your lattice energy decreases more. Yeah, so the decrease of lattice is larger. Okay, if you apply the formula, okay, the solution, what the value of the solution will give you, the enthalpy of solubility increases. So the enthalpy of solution is going to become more negative. So when it becomes more negative, okay, what happens? Okay, it is going to actually make the solubility increases. So this one, okay, you need to remember. Later, maybe we might apply this over here. So I'll just move on. So you see calcium hydroxide is slightly soluble in water. So calcium is at the top. Yeah, calcium is at the top. And then they say write an equation to show the dissociation of calcium hydroxide in aqueous solution. So we know that calcium hydroxide, okay, it must be solid, yeah, because dissociation. So it's going to dissociate, okay, to give you calcium 2 plus, okay, aqueous, okay, plus 2 moles of OH minus, which is aqueous. Okay, so this is going to be to show the dissociation, and do remember they are partially dissociated, so therefore, okay, we are going to or we say sparingly soluble. Yeah, so we actually use the reversible sign. Okay, calculate the solubility in mole per dm cube of calcium hydroxide, and solubility product is given. Yeah, so this is very interesting. Okay, because okay, you need to apply, okay, the Ksp. Okay, if you look at Ksp, okay, Ksp, if we write, okay, Ksp is actually Ca2 plus, okay, concentration, okay, times the concentration of hydroxide, which is going to be to the power of 2. Okay, but solubility, okay, you just need to write down in terms of X. So I will use this X over here. Or if you want, I think just to make it different than the marquee key, I will just use Y. Okay, if this is Y, okay, it will give you 1 mole, will give you Y, yeah, 1 mole to Y. So I'll just use Y. Okay, if that, the solubility is going to be Y, okay, this is going to be 2 times of that, yeah, so it's going to be 2Y. Okay, so the amount is going to be double. Okay, so if I want to write down in or to calculate, okay, the solubility, okay, solubility, I calculate, okay, by using the 5.02 times 10 negative 6 equals to concentration of Ca2 plus is going to be Y. Okay, and then the OH minus is actually double 2Y. So I will write down bracket 2Y. Okay, and that value is going to be to the power of 2. Okay, do remember this. Okay, but we don't write this one as 2 over here. Please remember this. Yeah, so this one you need to take note. Okay, so once you get that, we just want what is Y, solubility. Yeah, so Y is going to be, okay, times 4Y squared. You will get 4Y to the power of 3, which is going to be 5.02 times 10 negative 6. You just need to find the value of Y, which is 5.02 times 10 negative 6, divide by 4, okay, then cube root. Okay, so you do this, okay, and you should get the answer, okay, as Y, which is going to be, if you look at this value, okay, I will select maybe 1.08 times 10 negative 2. Okay, as you're following me, you can also check, okay, in your calculator, whether you get this answer. Yeah, so I will actually write it down as 1.08 times 10 negative 2. Okay, if you have any question, just feel free to interrupt me anytime. Yeah. Now, so suggest, okay, how the solubility of calcium hydroxide, okay, in aqueous sodium hydroxide compares to its solubility in water. Yeah. So now, okay, you put calcium hydroxide, okay, in sodium hydroxide aqueous. Okay, sodium hydroxide, they have NaOH. They give you Na plus and OH minus. Okay, and do remember water. Yeah, water is going to be H2O. Partially, they will give you, okay, solubility product, Josh. Yeah, Ksp is solubility product. So it will give you H plus and then OH minus, which is going to be partially soluble. Yeah, you do not have a lot of amount of OH minus or H plus. So in comparison, you have more OH minus here. Yeah. So if I put calcium hydroxide into sodium hydroxide solution, and if I put it in water, okay, what I will have is, okay, we know that calcium hydroxide, okay, we have this equation, okay, calcium 2 plus 2 OH minus. Okay, when I put them in this particular solution, okay, I will notice that there is going to be a presence of OH minus, which is what we have learned as common ion. Yeah, the same ion. So the common ion effect will take place where your concentration of OH minus is more. Okay, if your concentration of OH minus is more, okay, what will happen? The position of the equilibrium will be shifted to the left. Okay, when the position of the equilibrium is shifted to the left, you are going to form more precipitate of calcium hydroxide. So it means that if you put the calcium hydroxide in sodium hydroxide, okay, you are not going to have a very good soluble calcium hydroxide. It means the solubility, okay, the solubility of calcium hydroxide decreases, okay, in NaOH because of the common ion effect of OH minus in NaOH, which makes the position of the equilibrium shifted to the left to form more solid or undissociated calcium hydroxide. Okay, that is going to be my explanation. Now, some of you might be asking, okay, how about in water? Water contains OH minus also, yeah? Okay, this one we are comparing between water and sodium hydroxide, okay? But the amount of hydroxide ions that is existing in water is going to be too little, yeah? So in comparison to amount of hydroxide that you have in sodium hydroxide. So it means that you are just comparing between water and sodium hydroxide. So you do not need to mention about that. Okay, so in water, yeah, that is the standard. If you go and put in sodium hydroxide, what will happen? Yeah, so it means the solubility in water, yeah, that is the certain solubility, or you can say, solubility is this particular value that you have calculated. Okay, but if they ask you to predict the solubility value, okay, when you put in sodium hydroxide, then your solubility is going to become less. So you are going to predict a value which is less than 1.08 times 10 negative 2. Yeah, so that is the prediction. Okay, there is different way of asking question. Yeah, so if they ask you predict what will happen to the solubility in form of number or something, or suggest a number, the value that you might be able to suggest is going to be maybe 1.08 times 10 negative 3 times 10 negative 4 times 10 negative 5, or in general less than 1.08 times 10 negative 2. Yeah, if they ask you in that way. yeah, and you need to explain, yeah. So there is no need to explain between water and sodium hydroxide. The same you can see over here, okay, in the answer key. They say less soluble, okay, we did it, yeah. So we say the solubility decreases, so that's going to be the answer, okay, 1 mark. And then they say that it decreases as equilibrium shifted to the left, okay, so decreases because equilibrium shifted to the left, okay, done. And then common ion effect also, we actually mentioned common ion effect is also done. And or they say decreases, okay, because OH increases, causing the Ca2 plus OH minus to exit is Ksp. I didn't mention that, yeah, but that is not compulsory. They say or, yeah. So we did more than what is required also, yeah. So as long you mention that, okay, you will get the 1 mark. Okay, so total, okay, this is question number 1 is done, yeah. So it's going to be total 7 marks. Okay, let's go on to question number 2. Now for question number 2, okay, you can see that, okay, explain why chromium complexes are colored. This one, the moment you see something is colored, check first whether they are transition element or not, yeah. Chromium, if you check, yes, they are transition element, yeah. So if it is transition element, there are certain things that you need to follow, which I mentioned to you last time. But do remember, okay, because the change of syllabus, I will include certain parts that is not found in the marking key, yeah. Please remember this, yeah. So I will include certain parts, okay. So here you see the common one. I'll just list down what normally we will find from the marking key. They will talk about d orbital splitting, yeah. So d orbital splitting, so they will mention, okay, the electron become excited, okay, or promoted from lower energy level to higher energy level. How they are promoted? By absorbing the frequency of light, okay. So once your frequency of light is absorbed, okay, you are going to see complementary color is seen, yeah. So this one is common. I think you would have seen this many times, okay, even in the 2 years papers, the previous 2 papers that we have done, you would have seen the same thing. And you can see it's 4 marks, okay, but I want you to learn additional points, okay. Rather than simply saying d orbital splitting, I want you to include, because of the new syllabus, there are new terms that is included. The d orbital splitting into 2 non-degenerate orbitals. Okay, non-degenerate orbitals means wrong spelling, yeah. Non-degenerate orbitals means they are having different energy. Okay, that is the first thing that I want you to mention. Another thing also, yeah, depending on the complexes, okay, whether they are octahedral, okay, or whether they are tetrahedral, okay, they have different kind of splitting. In this case, they didn't specify, so no need to write, okay. But in future, if you know that it is tetrahedral complex, or if you know it's going to be octahedral complex, then you should know, okay, that the splitting, we have total of 5 orbitals in D, yeah. So 5 orbitals in D. So the octahedral, I'll tell you how to remember. Octahedral, they look like this. Okay, so up and down, yeah, 6 coordinate bonds. So I want you to remember the up and down, there are 2. So I will just say, okay, the octahedral, there are 2 orbitals at the higher energy level, high energy, and 3 orbitals at lower energy level. This one I already mentioned to you last time, yeah. So tetrahedral is the other way around. 3 orbitals are at higher energy level. Okay, I want to include this because, okay, it is mentioned specifically in the new syllabus. Yeah, so I doubt, yeah, so they might actually include this as points, yeah, and remove certain things like frequency of light absorbed. They make it combined with complementary color. We don't know, yeah. So let's actually be safe, yeah. So in this particular question, yes, it's not suitable to explain about this, but other questions maybe you can apply. Okay, so these two orbitals, okay, at lower energy level. Okay, lower energy level. So you can actually include that, yeah. So in the end, okay, I will just, for this particular question, I will include this one only. Okay, and then I will say the electrons will get excited and promoted. Okay, fine, no problem. Okay, frequency of light is absorbed. Okay, yes, no problem. And then complementary color is seen. Okay, or frequency of light absorbed. Okay, or energy. Okay, is absorbed. Okay, up to you which one you want to use. Okay, but these are my points. Okay, there are 4 points over there. So I don't think so I need to rewrite this again. Yeah, so I think the points are there. You can just put it in terms of sentences. Yeah, but if you look at the marking key, okay, so they say that they have complexes with 2 different energy levels. You can see DD or splitting orbital. So this one, okay, I told you 2 non-degenerate orbitals might be included in the future marking key. Yeah. So they say or is okay lah. So then number 2 is going to be your electrons move to the higher d orbital. So remember I told you excited or promoted, you explain, yeah, electron jumps up to higher. Okay, so promoted or excited, or there are other ways of saying. So if you write down in sentences, electrons get excited or promoted from lower energy level to higher energy level. You can do that. Yeah, you can just write down that. And then, okay, you can see here, I mentioned about frequency of light. So you see frequency, okay, of light is absorbed. Okay, or the energy from visible region is absorbed. Yeah, so up to you. Okay, I told you I use frequency of light, or if you want to write energy is absorbed, it's up to you. And then color is seen complementary. Yeah, so color is complementary, color is seen. Yeah, or you can say the wavelength or frequency or the color not absorbed is transmitted or reflected or seen. Yeah, up to you how you want to write. Okay, but I remember all these points because it's like a script. You know, every single time they ask you this question, these are the things that are available that I have even memorized it already. So you can do the same thing. Yeah, but the new thing that I'm actually asking you to add is this one, the 2 non-degenerate orbitals. In case, okay, in case they ask more, okay, you might want to include this as well. Yeah, if you know it's octahedral or tetrahedral and so on, you include that. How to remember? I already told you octahedral. This is the shape. So I remember this way, up and down there are 2. So I just remember 2 orbitals are higher energy. Yeah, this is how I remember. Yeah, so I know tetrahedral is going to be the other way around. Yeah, so that is done. So B, 4 different compounds can be obtained, okay, when anhydrous chromium 3 chloride reacts with water, okay, under various conditions. When the sample of each compound are reacted separately with silver nitrate, different amount of silver chloride are precipitated. Yeah, so silver chloride, okay, is going to be a white precipitate. Okay, I hope you remember this. AgCl, white precipitate. AgBr, cream. AgI is yellow precipitate. Okay, hope you remember this. The precipitate leaves the complex, okay, PQRS in solution. So you have all this, okay. So the moles of AgCl precipitated, okay, so you have different number of moles, okay. And then the complex ion, okay, PQRS, and then property of the complex ion, non-polar, polar, polar, and non-polar, okay. So we have all this, okay, we have all this. So do remember, okay, the number of moles of silver chloride, okay, precipitated tells us about how many Cl are there in that complex ion. Yeah, so I hope you understand this. So you say they say that they are going to when anhydrous chromium 3 chloride, okay, this one, okay, this chromium 3 chloride reacts with water, okay, under different condition. Okay, so the sample, okay, you can see the sample reacted separately with aqueous silver nitrate. So the formula of the compound, you can see the compound, okay, these are the formula of the compound. And you can see that they have different number of moles of water, okay. And then what I can see is, okay, there are certain amount of AgCl, yeah, that is coming out. It means that, okay, if you have 3 moles of AgCl, it means that there are 3 Cl came out from that compound. Okay, 3 Cl came out from the compound. And if you see 2 AgCl, it means that there are 2 Cl came out from the compound. Yeah, 1 means there's only 1 Cl came out from the compound. So there are still 2 Cl in that compound. Yeah, I hope you can still see. Yeah, if you have this, okay, 1 of the Cl came out from this compound, so leaving behind, okay, 2 Cl over there. Yeah, so that is going to be the one that we'll actually talk about when we talk about the complex ion. That is the complex ion that we are talking about. So, okay, like from let's jump directly into it. Yeah, so we know that if you have, okay, if you are removing, okay, if you are removing 3 moles of Cl, okay, for P, you what is the complex ion? Let's actually write it down directly here. Yeah, so if you remove, then you will have Cr, okay, Cr, okay, what each of the Cl is going to be -1 charge. Yeah, so you remove 1, then it'll become +1. You remove 2, then it'll become +2. You remove 3, then it will become +3. Okay, so Cr, okay, bracket H2O stay 6, okay, and then bracket 3 plus. Okay, that is going to be the complex ion for P. Yeah, so the property of the complex ion, okay, they mentioned that it is non-polar. Okay, they say it's non-polar. Okay, so include the charges. Okay, I think you can include the charges, but basically this is non-polar. Okay, the complex ion is non-polar. Why? Because it's all going to be H2O. Yeah, the ligands are all H2O. So if I want to draw the 3-dimensional diagrams for that, it's quite easy. Yeah, so you just need to put the something like this. Okay, you can see from the marking key they didn't put, yeah, but normally I like to put this, yeah, when I draw. So 2 lines to show that it's coming out from the paper, okay, like this. Okay, another one is I like to draw like this, okay, to show it's going behind. Okay, and then, okay, you have water. Yeah, so the lone pair is coming from O. Yeah, so I'll just put water, okay, like this. Okay, if you want to put water also, it's okay. Yeah. That's my 3-dimensional diagram, okay, for the structure. I've missed out one. Okay. So you can see, okay, do remember they mentioned include the charges. I've already put 3 plus, so I'll just put bracket 3 plus. Because Cl is Cl minus, yeah, you keep on removing. So the next one, okay, is going to be, do always remember, okay, that, okay, they are going to have this compound is going to have 6 coordinate bonding, yeah, 6 coordinate bonding. So if you remove 2 Cl from here, okay, from here, so you will have, okay, Cr, okay, there is 1 Cl left, okay, and then there is going to be H2O5. Okay, so you see there are 6 dative bond over there. Okay, you no need to add anything. Okay, but you see that, okay, you remove 2Cl, okay, it means that this is going to follow the charge of 2 plus. Each one is -1. Yeah, so if you remove -1, then you get +1. Yeah, so you remove another -1, you get +2. Okay, so if I want to write down the for Q, okay, similar, I do see that there are 5 water. Yeah, so you decide which one you want which area you want to put. Yeah, for example, if I'm drawing, normally I will draw like this. Okay, I know that there are 5 H2O, so maybe I put all the H2O here, the 4 H2O first here. And then one of the H2O, maybe I'll just put one H2O here. And another one, okay, I put as Cl. Okay. Then when I draw, okay, do remember I told you, you need to show the position properly, the 3D structure. Okay, I will draw like this. And then, okay, I will draw that. Okay, just to show that they are going to go behind. Yeah. So this is going to be the structure as well, okay, for Q. And you can see I still need to show the charge. I have already calculated, it's 2 plus. Don't forget about the charge. Okay, +2. And then for R, yeah, so this one is done. Okay, let's actually move on to R. Okay. So the do remember, okay, just now all the 6 water then is non-polar, but now you see the 6 water is going to be no charge. Then Cl is more electronegative. So if Cl is pulling the electron to one direction, then of course they are polar. Yeah, that's why it's polar. Okay, so this one is related to polarity. Yeah, so this one under chemical bonding. Yeah, in AS. Okay, so let's actually move on. Okay, now here they remove one, okay, Cl. So you are going to have Cr, okay, so Cl2. Yeah, one Cl went out. So you have leftover H2O4. So if only one Cl went, then it's only +1. Okay, so this one I have 2 Cl. So this one, if you have 2 Cl, you this is normally what I do. Yeah, no need to think so much. Cl up and down. Yeah, and then the rest you put the water. Okay, so OH.
Sir, for compound R, I thought it had to be polar. If they're on like opposite sides, wouldn't the electronegativity cancel out?
Okay, this one, okay, let me check first. Yeah, why is polar? Because I think it should be cancelled out. Okay, should be cancelled out. Okay, but let's see first. Okay, let's see first, because I think I have a doubt. Okay, when it comes to this plus also. Yeah, because of this plus. Okay, normally very hard to say something that is having a charge is polar or non-polar. Yeah, so let's actually this one I'll check for you. Yeah, so here they say it's polar. Okay, let's see whether this one is a mistake. Okay, or maybe we need to adjust a bit. Yeah, so this one I'll update you. Okay, but according to what I see, yeah, Cl and Cl, they should be cancelled out. Yeah, there is no other factors. The only possible factor that might influence this is the positive charge. But if you look at the positive charge, then the similar factor would have applied for P. Yeah, but they say P is non-polar. Yeah, so that is actually something that I'm actually confused also. Yeah, so I will check for you. Yeah, but anyway, okay, this is going to be we'll come back into that. Yeah, so this one I'll just put. Okay, I'll check for you. Now, then the CrCl3, okay, there is one Cl went out. Okay, so you have, okay, CrCl2, okay, H2O4, okay. But here, okay, they mention about this one. I think I know what is the problem. Actually, no need to check. Yeah, they are both same. Okay, So what I did was, okay, if they cancel with each other, non-polar, okay, that will be more suitable to draw for compound S. Yeah, this should come over here. Then it will become non-polar. Non-polar. Okay. Is that clear, Josh? Okay, that will become non-polar. So if I copy this, okay, it's the same compound, but if I put the Cl in different position, okay, I will start to put the Cl in different position. If let's say I don't put the Cl here, okay, and I put the Cl over here, then now they are polar. This is what they want. So the question is correct. Because both of them are the same, okay, the same ion, okay. So depending on how you put, okay, it will be influence whether they are polar or non-polar. So if it is going to be put top and bottom, then it's going to be non-polar. If it is going to be put like something beside, yeah, then they are not going to be able to cancel each other out properly. So they are polar. So R is polar. So this is going to be the best answer. Okay, Josh, I think this one is clear already. Yeah.
Yeah.
Yeah. Now, suggest, okay, so now they're asking why complex ion S is non-polar. Okay, S is non-polar. Okay, because, okay, the Cl and Cl, okay, this one, before looking at the marking key, I'll tell you, yeah, normally suppose you mentioned about Cl is cancel out, but normally we need to tell what cancel out. The dipole moment cancels out. Yeah, dipole moment cancels out. But let's see what the answer. Okay, you see dipoles cancel. Yeah. So this one, okay, last time when I teach you, yeah, the reason why we say cancel each other out, yeah, that's much more easier to say, yeah. But the actual term that we supposed to use is going to be the dipole moments, okay, the dipole moments of, okay, both Cl atoms or ligands cancel each other out. And that is going to be, so dipoles cancel. Yeah, I think better to say dipole moments. Yeah. Now, the next part, okay, the structure of picolinic acid is shown. Yeah, so they have given you the structure. Okay, and then the conjugate base of picolinic acid is bidentate ligand. Yeah, so they say it's a bidentate ligand. It's going to be the conjugate base. Okay. So define the term bidentate ligand. I think this is very popular already. By now you should know. Yeah, they ask you to define. Yeah, in the, I think the previous two papers, they ask you to define what is monodentate ligand. One of it, I think they did ask you to define bidentate ligand also. Yeah, in that paper. So here, if you want to define the bidentate ligand, it's going to be a species, okay, that has two lone pair of electrons, two lone pairs of electrons that can form two dative bonds with metal or metal ion. And this is very important. Yeah, so you can see the marking key will be almost the same as well. Yeah, it can donate two lone pair or form two coordinate bonds or two dative bonds. So I'm using the two dative bond. Yeah, so two dative bond. Okay, two lone pair. Okay, two lone pair. Okay, and then two metal atom or metal ion. Okay, metal or metal ion. So maybe I need to include metal atom. Okay, so that is going to be how you get the 2 marks. Okay, and then draw the structure of that. Okay, so the conjugate base, okay, is a bidentate ligand. Okay, so the conjugate base is a bidentate ligand zine. Yeah, so this is acid. Okay, acid. Okay, the base. So normally acid will donate the H plus. Okay, so the base is the conjugate. So it's going to be the base that we are talking about is the one that were after they donated the H plus. So if I follow exactly what is given, okay, we are talking about CO2 minus. Okay, so this should be the bidentate ligand. Okay, but do remember the bidentate ligand. Okay, when they say two lone pair, you need to identify. Yeah, the lone pair are coming from where? Yeah, so if I specify this, okay, C double bond O and then O minus. Okay, I know that nitrogen, okay, they form 3 bonds, okay, similar to ammonia. Okay, they form 3 bonds, but nitrogen are going to be from group 15. Yeah, so they do have lone pair, okay, and nitrogen. And I know that oxygen also, yeah, oxygen, they are going to be from group 16. Yeah, so they should have 6 valence electron. Yeah, so here, okay, 2 electrons, okay, are being used over here. So they will have also another lone pair over here, and they will also have another like this as well. Yeah, so there are so many. Okay, so unless they tell us, yeah, which of the lone pair is being used. Yeah, but just take note, okay, there is also lone pair at nitrogen. Yeah, so let's actually move on. Yeah, so here they ask you to
Can
draw.
we
Okay. Yeah,
can we
John.
say that this is also polydentate?
But they said it's a bidentate. Yeah, so it can behave. Yeah, it can behave as polydentate. Okay, depending on the metal ion. Okay, so it depends. So it depends also on the structure of the molecule. You see that sometimes most of the times they don't actually form coordinate dative bond or dative bond with this and this together. Yeah, because of the structure. Yeah, the structure, what they call it's the space. Yeah, it's not good enough. Yeah, so they have this restriction in space, so they normally don't behave like that. So in this case, they say they form bidentate. It means there are two dative bonds can be formed by this molecule. So they ask you to draw. So let's actually go one by one. If they didn't ask, then forget about it. So in this case, if I draw the structure, yeah, I'll just draw the structure. You do not need to include the lone pair of electrons. So I'll just copy first, and I will erase the lone pair, okay, because they don't want that. But make sure the negative ion is shown. Yeah, so this one. Now Z reacts, okay, so this molecule reacts with aqueous chromium 3 ions, okay, in a ratio of 3:1, okay, to form a new neutral complex. Okay, so ratio 3:1. Okay, so they are going to be Z. There are three compounds on Z with one molecule of chromium ion. Yeah, so it means that I'm just expecting the coordinate bonds. The number of coordinate bonds should be 6. Yeah, if you have 3, yeah, it means 3 means it's bidentate. 3 times 2, yeah, so it should be 6. So we are looking into octahedral complex. Okay, so state. Okay, that's why you see when I'm already forming in my mind. Yeah, that is what they are actually asking. So they say that there are 3, yeah, 3:1. So this is 3. So it means 3 bidentate. So there should be a total of bidentate 2 dative bonds. So if you have 3, then 3 times 2, 6. Okay, the coordination number is going to be 6. Okay, what is coordination number? Number of dative bonds forming a number of dative bonds surrounding the metal ion. Yeah, not the dative bonds forming from the ligand. No, yeah, the surrounding. So doesn't matter if it is bidentate, we count total. Yeah, total is 6. Okay, so the geometry is going to be octahedral. Okay, so that is what they want. Yeah. If they ask more, then we'll decide more later. Yeah. So this one, there is the next question. They say that it decomposes readily on heating, okay, to give you this compound steam. So it means water in form of gas, okay, and inert colorless gas. So if it is going to be inert, yeah, the only thing that is inert over here is going to be nitrogen gas. Okay, so you get this. Okay, so deduce the oxidation number. This is quite simple. Yeah, oxidation number of chromium. Okay, this is going to be a very important concept, yeah, under redox. Okay, so if you want to answer this question, there is some shortcut. Yeah, so ammonium is going to be +1. Okay, so it's ammonium 2, it means we know that Cr2O7 is 2 minus. Yeah, no need to count everything. Okay, so here we know that we can just calculate together. Okay, so just like this. Okay, so if I put I want the oxidation number of chromium, I just put X. Okay, so X 2X. Okay, 2X plus 7 times -2. Oxygen is always -2 equals to -2. This number. Okay, 2X minus 14 equals to -2. 2X equals to -2 plus 14, which is 12X is going to be +6. Okay, so the oxidation number is +6. Here, 2X plus 3 times -2 equals to 0. Okay, and then, okay, you just need to calculate further. Okay, so it's going to be 2x minus 6 equals to 0. 2x is 6. X is going to be +3. So +3. Okay, don't forget to put the plus. Okay, you can see yourself. Yeah, must be plus. Yeah, don't go put 6 and 3 over there. Yeah, very important. And then write an equation for the thermal decomposition. Yeah, they have already given you some information. So just use the information given. So you just need to balance it. Yeah. So Cr2O7, okay, decompose means no need to add anything. Yeah, so you just put like this. And then they are going to give you Cr2O3, okay, and then plus steam, okay, H2O gas, okay, inert gas, so this is going to be gas. So Cr2O3, okay, is going to be solid. Okay, I don't think so it's going to be aqueous because water is going to be releasing in form of gas. Yeah, so it's solid. So decompose, normally decomposition will be something that is solid. Yeah, so if you don't remember, you can say that when you heat up sugar, yeah, what will happen? It will decompose, but it will give you a solid. Yeah, so solid. So it means thermal decomposition normally will give you a solid. Yeah. So in this case, okay, we just need to balance this. Okay. If I look over here, nitrogen is balanced. I can balance it later. Cr2 is balanced. Okay. Hydrogen, okay, I do notice the hydrogen on the left is 8. Yeah. So I need 4. Okay, 4 over here. And if I put the 4 over there, then I will notice that my oxygen, okay, is going to be on the left is 7. Okay, on the right is also good, 7. Nitrogen is 2. Okay, I think everything seems to be correct, but I'll double check again. You see, nitrogen is 2. Okay, nitrogen is balanced. Hydrogen is 8. So hydrogen is 8, it's balanced. Cr2 balance, okay, then oxygen 7 balance, okay, balance with oxygen, okay, correct. Yeah, so that is going to give you the 1 mark. Okay, double check every single time. Yeah, so that is going to be done. Okay, 15 marks. Okay, so question 2 done. Okay, so let's move on. Okay, now it's going to be 9:46. Okay, I will stop the recording for a while. Okay, define the term transition element. Yeah, so transition element, okay, when you want to define, okay, make sure, yeah, there are certain points that you must mention. Yeah, it's going to be the element that can form, okay, elements that can form, okay, one or more, okay, one or more ions, okay, one or more ions, okay, with incomplete okay, d orbitals. Okay, this is going to be element, okay, that can form one or more ions, okay, with incomplete d orbitals. Okay, so if you look at the term transition elements, okay, not all, okay, elements, okay, are going to be transition elements. Okay, so if you if I quickly refresh your memory, okay, about transition elements. Okay, so transition elements, okay, I'll just quickly get my periodic table over here. Okay, so if you look at the transition elements for period number 3, yeah, so you have scandium, yeah, scandium, titanium, and so on, and ends with zinc, yeah. So if you look at this scandium and zinc, all these are going to be D block, under D block. Okay, but okay, all the elements in between, okay, they are considered to be transition elements. Okay, but okay, scandium and zinc, okay, they are not considered to be transition element. They are not considered. Okay, why they are not considered? Because okay, scandium, they will follow the 4s2 3d1. Yeah, if you follow the argon 4s2 3d1. This one will follow the argon 4s2 3d10. Okay, so the stable ion, okay, for scandium, okay, is going to be 3 plus. Okay, scandium will always form scandium 3 plus. If they form scandium 3 plus, okay, what will happen? Okay, the d orbital also, the 2 electrons, okay, from the 4s, and then 1 electron from 3d will be removed. Yeah, so you are going to have argon only. Yeah, so that is going to be the d orbital is not there. Yeah, it must be partially filled. So this one, no, yeah, scandium will not be the transition element, and they will not give you any colored complex. Okay, because even though there is going to be d orbital splitting, there is no electron there. Yeah, so there is no electron for it to jump. Yeah, so here, okay, for zinc always forms zinc 2 plus. Okay, if zinc 2 plus, the electron, it's going to be, they will follow argon 4s0 3d10. So 3d10 is complete. Okay, the d orbitals are complete. So if they ask you zinc chloride, for example, zinc nitrate or zinc chloride, yeah, why the color of the complex is going to be white, yeah, not colored. The reason is, even though there is d orbital splitting, yeah, the orbitals are full. Okay, the electrons cannot be promoted from lower energy level to higher energy level, so they don't absorb the frequency of light. Yeah, so they are not going to give you a colored complex as well. Yeah, so that is the reason, yeah, why zinc and scandium are not included as transition elements. So I just put this, okay, as a note, okay, related to that. Yeah, so I'll just put it here. Okay, now, so state how the melting point and the density of iron, okay, compared to calcium. Yeah, iron is going to be transition metal. Yeah, calcium is going to be group 2. Yeah, so if you look at the periodic table, if you have the periodic table, okay, I have the periodic table here. Okay, I'll just tell you the position, yeah, of Fe. Okay, Fe is in period number 3. Okay, and calcium is also going to be period number 3. So group 2. Okay, calcium is group 2, period number 3. Okay, this is going to be under this is 3D 1 2 3 4 5 6. Okay, this is 3D 6. Okay, it means if you follow the periodic table, okay, it's somewhere in the middle, yeah, of the period 3. Okay, so state how the melting point and the density compare to calcium. Yeah, so of course, okay, they are going to be as you move, okay, across the periodic table, yeah, group 1, group 2, group 3, the metallic property, yeah, supposed to be increasing, yeah. So if the metallic property is increasing, your melting point supposed to be higher, yeah. So the melting point of iron, yeah, melting point of iron is going to be higher than melting point of calcium. Okay, this is why, okay, the reason is going to be iron is more metallic. Okay, the metallic property is going to be more metallic because it's going to go more towards to the right. Yeah, so to the right. So the more it means from group 1 all the way to group 3. Yeah, so the more right you go, yeah, towards the to the right, you are going to have more metallic property. Yeah, so this is metallic bonding. Yeah, metallic bonding, if you want to remember what is that, is the bonding between the delocalized electrons and the metal ions. Yeah, so that is going to be the metallic bonding. So melting point is higher because of that. And then, okay, the density, yeah, do remember the density of transition metals are going to be greater. Yeah, the density is going to be greater. Okay, as you go also across the periodic table, you should know that the radius also decreasing, but the radius for the transition metal, they don't decrease that much, but density is quite high, okay, compared to calcium. Yeah, so density is going to be higher, okay, for, or density for iron is more than density of calcium. They didn't ask you how or explain, state. Yeah, so it's okay. Now define the term standard reduction, standard cell potential. Okay, standard cell potential, okay, is going to be, E cell is going to be the potential difference. Okay, the potential difference between, okay, two half cells. Okay, between two half cells. Okay, in solutions, okay, in solutions. Okay, because do remember there are two ways of asking this. Yeah, standard cell potential and standard reduction potential. Yeah, standard reduction potential, then you compare, that is the potential difference between one half cell and another half cell is the hydrogen. Yeah, so you compare, that is standard reduction potential. But this one is the standard cell potential. So it's a potential between two half cells. Yeah, so no need to be hydrogen. Yeah, it can be any half cell in comparison to half cell, hydrogen half cell. So two cells. Yeah, so the potential be a difference between two half cells in solution, okay, of 1 mole per dm cube must be 1 mole per dm cube. Yeah, because standard condition. So under standard condition. So that is going to be 2 marks, okay, 2 half cell, okay, 1 mole per dm cube. And then they say draw a fully labeled diagram of the apparatus that can be used to measure the cell potential, okay, of copper 2 plus. So you see this one is metal ion, okay, and then this is ion and ion. Okay, so I hope you remember how to draw all this. Okay, metal and metal ion. So metal and metal ion. So you just put the, okay, you just put the something like this. Okay, so this one maybe I put copper. Okay, so here inside I put copper 2 plus. Okay, so I just put copper 2 plus. 1 mole per dm cube. Aqueous. Okay, then this one I want to put ion and ion. So ion and ion also I still need to have a proper electrode. The electrode what I use, okay, the electrode cannot use Fe. The electrode you must use platinum. Okay, so the platinum, okay, I will just put over here platinum. Then this one, the solution will have Fe3 plus and Fe2 plus. So I'll just put Fe2 plus and Fe3 plus aqueous 1 mole per dm cube. Then, okay, it's going to be a cell potential. Yet you want to measure the cell potential. How do you measure the cell potential? By using voltmeter. Do you need to put the battery? No need, yeah, because this is going to be we are measuring between different standard reduction potential. So it means there is going to be, this is going to behave as a battery. So you do not need to put a battery over here. This is not electrolysis, yeah. So this is no need to put battery. But now, okay, if you put like this, it's not complete, yeah. So you need to use, okay, salt bridge. Okay, a salt bridge must be used. So you need to tell what do you use for the salt bridge. Yeah, so I use the filter paper soaked with what? Okay, sodium. Okay, if I remember correctly, sodium nitrate. Yeah, sodium nitrate is always, okay, sodium nitrate there. So here they just put salt bridge. Okay, so if I'm not mistaken, it's sodium nitrate. Okay, cannot be chloride, yeah, because if let's say you're using any, like for example Ag plus, yeah, so Ag plus will give you AgCl, so the filter paper will not work, yeah. So filter paper soaked, okay, in NaNO3, okay, what is this actually? This is salt bridge. Okay, this will do it, yeah. So sometimes we just salt bridge is to they have three functions, Josh. Okay, so one is going to be, okay, one salt bridge. They have three functions, 1, 2, 3. Okay, complete the circuit. So how do they complete the circuit? Yeah, because the circuit must be completed, because to allow the movement of, do remember, electron, they move along wire. Yeah, so salt bridge, okay, to allow the movement, not electron, the movement of ions. Okay, when the ion moves, okay, then the electricity will be moving. Yeah, so to complete the circuit, to allow the movement of ions, one more I forgot. Okay, but I think, okay, this is already good. Yeah, complete the circuit to allow the movement of ions. Okay, another one, sorry. Number 3 is going to separate, okay, to separate the two electrolytes. So if you don't use salt bridge, okay, the two electrolytes must be mixed together, which we don't want. Yeah, the copper 2 plus and Fe2 plus, Fe3 plus, okay, they might actually have the anions that might react with each other. Yeah, we don't want that. Okay, so there are three functions, okay, for salt bridge. Let's move on. Now the reaction, okay, of this S2O8 2 minus, okay, and I minus is catalyzed by adding a few drops of Fe3 plus. Okay, so use equations, okay, to show the catalytic role of Fe3 plus in this reaction. Let's actually look at other information given. Yeah, so I think here they say the reaction between S2O8. Yeah, so I think it's a separate question. So here, okay, you need to remember, since, okay, you are not going to be given with the data booklet. Yeah, sometimes this is what I told you. Yeah, data booklet given, there are advantages, there are also disadvantages. Yeah. For this question, okay, if the data booklet is given, it will serve as an advantage. Why? Because if you do not know what will happen to S2O8, you can still refer to the data booklet and guess. Yeah, you can guess. But now, okay, because the new syllabus is there, okay, I will ask you to memorize, yeah, or to be independent, yeah, to be independent on what will happen. okay, S2O8, okay, they will always give you SO4 2 minus, okay. So all this information for the E value, okay, will be given, okay, in the question itself. Yeah, for this, we still need to refer to the data booklet. Yeah, if you refer to the data booklet or they give you some information, okay, you will get something like S2O8, okay, gives you SO4 2 minus. Okay, I will quickly look at the data booklet for you. Yeah. So let me get the equation. Normally this one will be given for you. Okay, so hold on. S2O8. No password. No password, no password. S2O8, 2 minus plus 2 electron to give you 2 SO4 2 minus plus 2.01. Yeah, so this one I took it from the data booklet. Yeah, so I have this. Yeah, I have this. Okay, and it will help me to answer this question. Yeah, and then they are going to be added with few drops of Fe3 plus. Yeah, so Fe3 plus. Okay, if you look at Fe3 plus, okay, sometimes students will be wondering, yeah, this one may be disadvantages of using data booklet. Students will be wondering which one to use. Fe3 plus, they can give you Fe2 plus. They can also give you Fe. Yeah, which one should we use? Yeah, which one should we use? So in this case, okay, I think, okay, because we are dealing with Fe3 plus and Fe2 plus, okay, I'm not thinking of using Fe. Yeah. So I'm going to use Fe2 plus. Okay, so this is how I determine. Yeah. So they are going to be added with electron to give me Fe2 plus. Okay, so this one I quickly get the value. Okay, even though they didn't ask us yet. Okay, but if they ask, then we are prepared. Yeah. So this one is 0.77. Okay, plus 0.77. Okay, all the information are there for us. Yeah, so now we just need to use the equation to show the catalytic role of Fe3 plus. Okay, so what happens over here is, okay, you are going to react. Okay, you are going to react S2O8, okay, 2 minus, okay, and then they are going to give you, okay, this is plus 2 electron, they are going to give you 2 SO4 2 minus, okay, which is going to be I'll just put, okay, I think not required, so I'll just don't put, yeah, I'll just put over here. So this is the one equation, and then, okay, you have the I minus, okay, it will react with the I minus. This I minus, of course, they are going to actually lose the electron to give you this 2I minus to give you I2, okay, plus 2 electron. You should know this, yeah. This one no need to refer to the data booklet or what. You should know this, yeah. These two will happen, yeah. But do remember, okay, they say that we need to show how, okay, the Fe is going to behave as a catalyst, yeah. So you cannot simply add these two equations together. I'll show you what is the students will do. Students will add these two equations, and then they say S2O8 2 minus, okay, plus 2I minus, cancel the electrons. You get this plus 2 SO4 2 minus, settle. This is not what they want. Okay, this is not what they want. So what you need to tell, okay, what you need to do first, okay, is going to be related to your Fe3 plus. Okay, do remember, if you look at the data value, okay, Fe3 plus, okay, you want this, okay, you want this first equation to go to the right. Okay, so it's 2.01. Okay, it's 2.01. And of course, okay, if this is 2.01, this is smaller value. Of course, they will this one will go behind. Okay, this one is something that you need to know. So it means that, okay, S2O8 actually reacts with Fe2 plus. This one for those people who do not know. So if I put it over here, S2O8 2 minus, okay, they will react, okay, with Fe2 plus. So if I write down Fe2 plus, okay, they will give me Fe3 plus an electron. This is plus 2 electron to give me 2SO4 2 minus. They didn't ask you to calculate the E value. Yeah. So I need to write that equation first. Okay, I need to write that equation first. So first, balance the electron. Yeah, so just put times 2, times 2, times 2. Okay, when I add this one will cancel. So it means that the first equation is S2O8 2 minus plus 2Fe2 plus. It will give me 2SO4 2 minus plus 2Fe3 plus. This is my first equation. Okay. The second equation, okay, must be something that involves this I minus to go to that direction. Okay. So that direction, if you go and look at the E value, it's okay. You will get the same thing. Yeah. If I just quickly get the E value for that, okay, I minus, okay, I2, okay. If you just follow the I2 plus 2 electron to give me I2I minus, okay, this value is 0.54. Okay, 0.54. So now, okay, if I want this I minus to go that side, it means that this is negative 0.54. Now, if this is negative 0.54, or just look at this value only, yeah? Okay, I hope I'm not confusing you guys. Okay, if you just look at this value and then you compare with Fe3 plus electron to give me Fe2 plus, which is going to be 0.77, you will notice that, okay, this is going to the right, more positive. Okay, and this should be going to the left, which is what we want. Yeah. So it means that I know that, okay, when I add or when I change the equation to this, which is this, it must be reacting with what? It must be reacting with Fe3 plus, not Fe2 plus. Okay. For those who don't understand, I write down again there. So 2I minus to give me I2 plus 2 electron, okay, 0.54 negative. So it means that this one is reacting with Fe3 plus. Okay, so this is actually telling you which one will react with Fe2 plus, which one will react with Fe3 plus. Yeah. Okay, so this one, okay, I will erase first. So this I know that 2I minus, okay, will give you I2 plus 2 electron. Fe3 plus, okay, plus electron give me Fe2 plus. Okay, the E value, they didn't ask you to calculate. It's okay, just leave it. So this one I need to times by 2. I want to eliminate the 2 electron when I add. Yeah, I am going to eliminate the 2 electron. I will have 2I minus plus 2Fe3 plus to give me I2 plus 2Fe2 plus. Okay, this is equation number 1. This is equation number 2. And what will happen if I add these two equations together? You see the Fe2 plus to produce Fe3 plus. Fe3 plus is being used to give you Fe2 plus. So you can see that, okay, you are removing, yeah, it means that this is going to show you the catalytic role of Fe3 plus, yeah. So this is going to be what is going to happen, yeah. Okay, so if I look at it, okay, the 2I minus, okay, 2I minus is reacting with Fe3 plus, okay, that is the catalyst, the first time it is used, okay, and then it is producing Fe2 plus, but that Fe2 plus is being used again, and produce Fe3 plus. So catalyst looks like as though they are not used, yeah, but they or take part in the reaction. So they didn't ask you to write down the full equation, but if you write down the full equation, this is the full equation. Yeah. So these are the two equations that you need to put. Okay. But I think when giving numbers also, the first equation should be, this should be the first equation because reacting with Fe3 plus, that's the catalyst. Yeah. So this should be the second equation. Okay. So this one will give you the 2 marks. Okay. Now the next question is, okay, Fe3 plus, okay, they can oxidize I minus, okay, and FeCN63 minus cannot oxidize I minus. Okay, let's actually see why, yeah, or use the E value. Yeah. So you see Fe3 plus, okay, plus electron, they will give you Fe2 plus. Okay. So just now I put the value which is going to be positive 0.77. So if you look at I minus, related to I minus means I2 plus 2 electron give you 2I minus, which is 0.54. Okay. Now you can see here, okay, if it is going to be more positive, yeah, then they will go to the right. They will go to the right. This one will go behind. Yeah. So you see Fe3 plus can oxidize I minus, which is correct. I minus is going to be -1 to become 0 is oxidized. Yeah. So this is going to happen. Yeah. This is going to happen. But okay, they mentioned that FeCN6. Yeah. So let's actually look at something related to FeCN6. Then 3 minus over here. Okay, let me look at the data booklet whether they have this value or not. Okay, if I look at the value of Fe, you can also look at the data booklet. Okay, I found out the value. So I have FeCN63 minus plus electron to give me FeCN6 4 minus 0.36. All this data, you can get it from your data booklet, yeah? So I'm not showing you here, yeah? So I get this value, okay? And now, okay, I'm talking about the same thing, which is going to be I2 plus 2 electron to give me 2I minus 0.54. Now, you see the value, which one is more positive? Okay, this value is more positive than 0.36. If it is more positive, they go here. Okay, but what is your aim? Your aim is to change I minus to become I2. Yeah, so it is not possible. Okay, it is not possible, and you need to explain why. Yeah, so it's not possible. Okay, what will happen actually is going to be this compound is going to change I2 to become I minus, not I minus to I2. Yeah. So we are going to use the E value to explain. Okay. So if you look at the E value, okay, you can actually, you include all these values. Okay. You show. Okay, like what I've shown over here, you can show all this. Okay. And then you say, yeah, using this, okay, you can say Fe3 plus, okay, can oxidize, okay, I minus, because, okay, the E value, standard reduction value of Fe3 plus, okay, Fe2 plus is 0.77 or more positive than E value of I2 I minus, which is 0.54. Or if you want to write down, if let's say you want to write down the E value, the E cell value, okay, the E cell value, okay, if you react, Okay, if they go to the right, this one is going to go to the left, negative. So 0.77, negative 0.54. Okay, this is going to give you positive 0.23, which is the E value is greater than 0. Okay, so the reaction is spontaneous. And the reaction is spontaneous. So you can write down like that. So you use the same method that I've used over here. Okay. So this cannot, okay, this FeCN63 minus cannot oxidize, okay, I minus, because, okay, you explain this FeCN63 minus, okay, the E value is 0.36 or less positive than 0.54 for I2 and I minus. Okay, so if you calculate the E value, okay, the E value also, they will go in front, this one will go behind. So if you calculate directly, if you want this one to go in front, okay, you want this one to go behind, then it's negative, so 0.36, negative 0.54. Okay, so if I find the difference, okay, 0.54, 0.36, okay, so 8, negative 0.8, 18, negative 0.18, okay, less than 0, non-spontaneous. Okay, I just explained everything, yeah, so it's up to you, yeah, which one you want to use. Okay, but you can always refer to the marking key, yeah, you can see whatever that I've written is all written over there. Okay, it's all written over there. So you just need to tell more positive or not. Yeah, then the negative 0.18 I have calculated. So some of you think, oh, should I calculate all this? Yeah, you should calculate all this. Yeah, you can see from the marking key. And then it's more positive than 0.23, which I have calculated also. The moment they see all this information, yeah, then only they will give you the mark. So don't do the lazy work of not calculating and just predicting. Don't, yeah. So the values must be there. Okay. So this one take extra time, okay, to analyze and give the answer properly. Yeah. Now the next question. Okay. When aqueous solution of S2O8 minus and tartrate ions are mixed, the reaction proceeds very slowly. However, the reaction produced quickly in the presence of Fe3 plus catalyst. The overall reaction is given. Yeah, suggests why the reaction is slow without Fe3 plus catalyst. So now we are actually suggesting why there is a need to have a catalyst. Yeah, so the catalyst, I think normally we say, okay, the presence of catalyst is going to because if it is without the catalyst, you need a very high activation energy. Yeah, but we cannot simply in A2 just give answer. It requires this because they have high activation energy. Yeah, you need to tell why they have high activation energy. Yeah, the reason why they have high activation energy is, okay, when you react between these two, okay, you can see both of them are going to be negatively charged. Yeah. So if you are bringing something that is going to be negatively charged, okay, they are going to generally repel. Yeah. So if you have a catalyst which is going to be positively charged, yeah, at least the activation energy is going to be reduced. Yeah. It will be reduced significantly. Yeah. So the main reason over here is, okay, both S2O8 minus and tartrate ions are negative charged. So they repel each other. Therefore, activation energy, yeah, you write down in full, activation energy is high. Don't go simply give answer activation energy is high. Okay, tell why. Okay, because if you don't tell or give two statement, you will not get the mark. Yeah, so because that's why you have this and. Okay, it means that doesn't mean that you have high activation energy, you will get correct. Both of these statements must be there, yeah, in order to get the 1 mark. Now, use the overall equation to deduce the half equation for the oxidation of tartrate ions, okay, to carbon dioxide and metanoate ion. Yeah, so use the overall equation to deduce the half equation. So I need to deduce the half equation. Okay, so they say it will give you CO2, okay, plus HCO2 minus. Okay, so this HCO2 minus CO2, okay, and then this one. Okay, so I have, okay, you know that C4, okay, C4, okay, of course, they are going to actually, we need to have 2 carbon, 4 carbon in total. So I just need to put 2 there, 2 there. So we just follow like this is okay. Yeah, so that one is no problem. Okay, the rest, okay, the rest is going to be, we know that S2O8 2 minus 3, okay, they are going to give me, when I see this, maybe if I put it as H plus, yeah, H plus, H2SO4, okay, so maybe I put this one, H2SO4, I put 6, cannot. Okay, there's water. Okay, so plus, okay, there is presence of water. Okay, so anyway, they are going to give me 6H plus and then 6SO4 to minus. Okay, they give you this. So here, okay, I need to predict. Yeah, I need to predict which one, okay, what equation, okay, that I will get, yeah, with S2O8. Okay, I think if we try to look at the others, okay, I can see here, okay, when I look at this, the previous equation, I have this, yeah, S2O8 plus 2 electron, 2SO4, 2 minus. I will try to use that. Okay, let me try to use that. S2O8, it will give you 2 plus 2 electron. It will give you 2SO4, 2 minus. Okay, that is one half equation. So when I have that half equation, okay, I know that this one is using 3. Okay, so if it is using 3, so of course, this one is 3. Okay, so this one is also times by 3, so 6. Okay, and this one is going to be times by 3. Okay, it's going to be 6 also. Which is, this one is well done. Okay, no problem. This one is done, no problem. We have done this, no problem. We have done with this, no problem. The only problem that we have over here is the H2O and 6H plus. Yeah, so this H2O and 6H plus, okay, must be coming from, okay, this here. Okay, must be coming from here. So this will be, okay, you need to write down, okay, plus H2O. Okay, so I put how many H2O? Okay, I just take this one, whatever I have, 2 H2O. And then, okay, they are going to give me 4H. Okay, and I see here another 4H. Okay, so I have 8H. Okay, if I have 8H, I have 2H here. So I must have 6H over here. So which is correct. Okay. Now, the final thing that you need to do is to balance the electron. And this one a bit difficult, a bit there, but you need to do it carefully. Okay, so I know that this one is 6 electron. Okay, so of course they already times, okay, to 6, yeah, times by 3. Yeah, so it means that the previously they supposed to have 2 electrons on it, so they times by 3. Yeah, so the reason that they times this with 3 because they want to eliminate the electron completely. So if you have 6 electron on the left, you must have 6 electron on the right. Then only they will cancel. If not, they are not going to cancel. This is the last part that you need to put. Okay, so you must have the 6 electron. Okay, once you add these 2 half equations, you will get this. If not, then you will not get the what is being intended over there. So all this, okay, must be there, and you can see, okay, we found out this. Okay, took some time, yeah, but it's actually something. I think even though we do it slowly, okay, it's very important, yeah, to understand. Okay, that now E. Complete the following table to show the structures of organic products formed when tartaric acid reacts separately with each region. Yeah, so you have tartaric acid, so I can see that they have alcohol group. Okay, I can see that they have carboxylic acid group. Okay, so the alcohol, okay, and carboxylic acid. So you see when you react with the LiAlH4 excess, yeah, so this is going to be a reducing agent. Okay, this reducing agent, if you look at alcohol, yeah, alcohol, the reducing agent, okay, if you alcohol cannot be reduced further, yeah, cannot be reduced further. So alcohol is not going to get involved over here, okay. But carboxylic acid, yes, yeah, carboxylic acid is going to be reduced, okay, to what? Okay, because primary alcohol, okay, they are going to be oxidized to become aldehyde. Aldehyde can be further oxidized to become carboxylic acid. So this carboxylic acid, they can be reduced using LiAlH4 in dry ether. Yeah, so that is going to be what's happening over here. Yeah, you are going to get a primary alcohol. Okay, so here, okay, what you need to put is going to be the structure of the organic compound. Yeah, so I'll just put the OH here. So this one, okay, the carbon, okay, this is going to change into it's like RC double bond OOH. Okay, they are going to be reduced, okay, into RCOH H. So that is going to be the primary alcohol that will be formed. Okay, so this carbon will still be there. Okay, that carbon will be still there, but okay, the remaining there will be 2H over there. The R will stay, so 2H, and then you have the OH. Okay, here, okay, and then here the same carbon. Okay, the 2H, and then you have OH, and then so if you look over here, they have completely used the skeletal formula. Yeah, if you want to change it into skeletal formula, the carbon and hydrogen are not shown. Yeah, so the final answer that I will show, okay, is going to be carbon 1, 2, 3, 4, 4 carbon. So 1, 2, 3, 4, 4 carbon, and then it's bonded to OH, bonded to OH. This one is bonded, this carbon is bonded to OH. I put OH. And then this 1, 2 second carbon, 1, 2 second carbon is bonded to OH. And then this carbon is also bonded to OH. Yeah. This is how you write down. Yeah, you just need to write down, okay, using this. Okay, so you can see from the structure as well. So the type of the reaction, this is going to be, of course, is going to be reduction. Jordan, okay? Okay, so first, okay, I write down this, okay, then, yeah, I will actually make it better. Yeah, so no need to actually straight away jump into skeletal formula. Yeah, but the final answer is this one. Similar way, okay, if I have this excess, okay, CH3COCl, yeah, this one you have to be very careful, okay, because, okay, this if you look at this alcohol, okay, alcohol, they do react with carboxylic acid, okay, to give you esterification. Yeah, but okay, alcohol, okay, can also react with acyl chloride to give you esterification at room temperature. Yeah, but if you look at carboxylic acid, okay, can carboxylic acid react with acyl chloride? The answer is no. They are not going to react with acyl chloride. So the carboxylic acid is going to stay. Yeah, the carboxylic acid is going to stay. The OH is the one that will react with the acyl chloride. So if I put it over here, ROH, they will react with, let's say, CH3COCl. They are going to give you R, okay, the H and the Cl will go out. So RO. So you have carbon, double bond O, CH3. You will get this. Okay. So if I put it over here, okay, if I follow the question, CO2H, then O, okay, the H is gone, okay. Then you just, the H is gone, so you have O, so you start with CO, okay, so C double bond O, then CH3, and then you bring it down. This one still CO2H, this O, again C, double bond O, CH3. Okay, this one, when you look at it, okay, it looks so complicated, okay. So you can simplify this, okay, let me make it smaller a bit. Okay, you can simplify this, okay, by writing it in this way. CO2H, then bonded to OCOCH3. You can write down like that. This one CO2H, OCOCH3. Okay, and what type of reaction is this? Okay, so this is, okay, even though it's you can say it's esterification, yeah. So the actual type of reaction is because you are removing the H and Cl, yeah, so it's going to be a condensation reaction. Yeah, does it mean the if I write down esterification is going to be correct or wrong? Okay, this one we will leave it to the examiner. Yeah, because here they say condensation and they didn't say esterification. Yeah, so you need to be very careful. Yeah, so if they didn't say heat under reflux, I think when I say excess of COCl2, normally under room temperature, yeah, esterification, yeah, will happen. Yeah, but this one is a type of reaction. Yeah, so I think the one that they are looking into is condensation. But if you happen to write esterification, still correct. That one depends on the examiner. Yeah, depends on the examiner. So that is condensation reaction. Yeah. Now, so tartaric acid, okay, reacts with amine 1-phenylethyl amine to form an ionic salt. Okay, so tartaric acid. So let's see what is tartaric acid again. Okay, so I erase this. Okay, 5 more minutes. Okay, copy and bring over here. So this one, okay, reacts with C6H5. So I'll just write down C6H5. And then, okay, you have CH, okay, CH, and then CH3, and then NH2. Ethyl amine, okay, ethyl amine. CH, CH, CH3, NH2. Yeah. So this is ethyl amine. Okay, one phenyl ethyl amine. One phenyl ethyl amine. Yeah. Okay. Draw the structure, okay, of the salt, okay, that is going to be formed in this reaction. So you are going to actually react. Yeah, of course, this one is going to be amine. Okay, amine is the one that is going to react. Okay, so the amine is going to react with what? Yeah, so this is very important. Amine is base. Okay, so they are going to react with acid. Okay, so the acid that we are going to have over here, okay, is going to be coming from the carboxylic acid. Okay, so you need to remember that. So the carboxylic acid is the H plus. Okay, they will be lost over there. So they say they react to form ionic salt. Draw the structure of the salt formed in this reaction. Include the charges. Yeah. So here, okay, I think draw the structure of the salt. Okay, the salt that is going to be formed, there are two types of salt. Okay, so they form ionic salt. Okay, P3 reacts with the amine to form ionic salt. Draw the structure of the salt formed in the reaction. So when I look at it, it's going to be the H plus. Okay, H plus. Okay, will go out. Okay, and then they will give the H plus to here. Yeah. So I do see two types of salt. Yeah. So they say to form an ionic salt. I don't know which one. So I'll just give both. Yeah. So I will have, okay, OH, CO2 minus, and then CO2 minus. Okay, so you are going to have CH3, H, NH3 plus. Okay, so these are the two. Okay, they react with phenyl, amine 1-phenyl phenylethylamine to form an ionic salt. Okay, draw the structure of the salt that form in this reaction, include the charges on the ions. Yeah, so on the ions. So I think it should be a better question. Yeah, they didn't phrase the question properly. So they want the both. Yeah, so here, even here, they say they want both. Okay, so I just put it over there. Okay, so it's correct. So draw the structure. So it doesn't matter. They write. Okay, we can draw. Still the same. Okay, so that is going to be the three questions. Okay, we have done. Okay, so it's already 10:45. Okay, number 4. Sample. Okay, of this copper. Okay, complex are reacted separately with excess aqueous sodium hydroxide and with excess aqueous ammonia. So this kind of question have been repeated many times, okay, under transition elements. So you need to know how to write the equation memorized. Okay, make sure you know the colors and make sure you know how to write the ionic equation and so on. So for the first one, okay, CuH2O6 with excess aqueous sodium hydroxide. So what will happen? Okay, so you are going to have, okay, 2 moles of OH minus, okay, will come in. So I'll just write down. Okay, so you have the OH. Okay, you are going to have. Okay, I'll rewrite this first. So you are going to have 2 OH coming in. Okay, and you are going to get CuOH2, and then 2 moles of H2O will be removed. Okay, so you have H2O4 bracket. Okay, so this one is going to be, you have previously you have 2 plus, okay, so now you are bringing in 2 minus, okay, so this is going to give you a neutral molecule, okay, a neutral complex, and you will have 2H2O over there, okay. So color and state of the copper containing species, so we know, yeah, this is going to be blue solution. So this is going to be if you have sodium hydroxide, yeah, hydroxide ion, yeah, when you mix and then you want to test for copper 2 plus ion, I think one of the popular question over here is going to be what will happen, yeah, if you test with sodium hydroxide. Okay, so this one is going to give you a blue precipitate. Okay, so this is going to be blue precipitate. So what type of reaction is this? Okay, so this is going to be precipitation reaction. Or if you look at it, it's going to be like something like a acid-base reaction, okay, to give you salt and water. Okay, so if you want to write down acid-base reaction also, okay, you can do that as well. Now, the next question is going to be reaction 2. Yeah, you have the same thing, a blue solution. Okay, you are going to react with excess aqueous ammonia. So if you use excess aqueous ammonia, you are going to get a dark blue solution or deep blue solution. Yeah, so color, okay, is going to be deep blue, and then the state is going to be solution, not precipitate. Okay. So ionic equation, okay, same. You just start with this 2 plus. So you are reacting with ammonia. So what will happen? Okay, you are going to have, okay, just now the OH, there are 2 moles going in. So this one is going to be 4 moles will be going in. So it's going to be Cu, okay, ammonia, that's going to be 4, okay, left with H2O, which is going to be 6, okay. And we know ammonia is going to be neutral. So previously it's Cu2 plus, yeah. And then now you have ammonia, okay, and water is also neutral. Ammonia is also neutral. So they are still going to be 2 plus. And then you're removing, okay, you're removing water. So I think this one is wrong just now. Okay, so the water is going to be, you're maintaining 2 molecules of water. And so you are removing 4 molecules of water, 4 moles of water. Okay, so this is going to be, if you look at it, a type of reaction. So this one is deep blue solution. So it's better if you want to write the type of reaction, it's going to be a ligand exchange. Yeah, so you're exchanging the ligand, okay, with the water ligand. Yeah, so you are going to just write down as ligand exchange is okay already. So the next question, okay, copper 1 oxide. So copper 1 oxide, Cu plus O2 minus, so it's Cu2O, yeah, is added to hot sulfuric acid. A blue solution X, okay, and a red brown solid Y form. Yeah. So if you add with H2SO4, okay, you are going to get a blue solution that is actually CuSO4. Yeah, copper 2 sulfate. Yeah, and then you are going to have, okay, a red brown solid. Okay, a red brown solid is going to be Cu. Okay, Cu. Red brown solid. Okay, so it's going to be Cu. Yeah, so it's I think it's going to be copper oxide plus H2O. Okay, I think Cu. Okay, cannot be CuO. Yeah, so it's going to be Cu. So if you balance this, okay, let's look at the balancing part. SO4 is balanced. Okay, oxygen. Okay, that is going to be, okay, if you look at it, okay, it's going to be CuO, but they didn't ask you to write down the equation. I think it's okay already. So no need to worry about balancing the equation. So identify, okay, a blue solution. So it's going to be copper 2 sulfate. So identify CuSO4. And then for Y, which is going to be a red brown solid, so it's going to be copper. Okay, so the type of reaction, okay, this is going to be, since we are talking about Cu is going to be Cu2O, it's going to be positive 1, okay, here is positive 2. If we look at this, this is 0. So you can see that the oxidation number is going to be, you can have oxidation and also you have reduction at the same time. So this is going to be a disproportionation reaction. Disproportionation reaction. Done. Okay, let's move on. So just to recall again, okay, if you have copper, okay, H2O6, okay, so it's going to be 2 plus, okay, you can react, okay, with OH minus, okay, and you can react with ammonia. So if you react with OH minus, you have CuOH2, okay, then H2O4, okay, and this is going to be neutral, yeah, so this is going to be solid, okay, so this solid is going to be blue precipitate and you are going to give you 2 H2O, okay, so this is 2, so this one, okay, this is 4, okay, so you are going to have CuNH3 4 H2O2, okay, so this one is still going to be 2 plus, okay, and then plus, okay, you have 4 moles of water, okay, so this is going to be a deep blue solution, okay, not precipitate, okay, this is going to be the summary of this equation. Now, number 5, dinitrogen pentoxide, okay, N2O5, okay, is dissolved in inert solvent and the rate of decomposition of N2O5 is investigated. This reaction produces a nitrogen dioxide, okay, which remains in the solution and oxygen gas. So I think they have given you the equation. Now, suggest what measurement could be used to follow the rate of this reaction from the given information. So from the given information, you have solvent, and I am producing oxygen gas, okay? So the moment you have gas being produced, okay, the easiest way is to look at, okay, measure the volume, okay, of the gas, okay? Measure the volume of the oxygen gas formed, okay, against time. Okay, so you can actually do that, okay. Now, for B, in a separate experiment, the rate of decomposition of N2O5 is investigated. So you have, okay, the graph shows the results obtained. So this is going to be, you have concentration against time. Yeah, concentration against time. Now, this concentration against time, okay, this is going to be N2O5, okay, which is going to be the reactant. So you can see that, okay, it's a curve, okay, and it's decreasing, yeah, because it's reactant, okay. When we look at, okay, we have two types of graph, okay. One is going to be rate, okay, rate versus concentration. Okay, rate versus concentration, and we have concentration versus time. Yeah. So if you look at the way we represent this, okay, we know that, okay, rate equals to K. Then we follow like this is going to be first order. Okay, if you have zero order, then K. Okay, then we have first order. Then we have second order, and so on. So if you look at this graph, okay, if you have zero order, then it's K, just like this. Okay, so it's just K, and then that's zero order. So if it is going to be first order, then the graph is going to be following a straight line like this. Okay, so this is going to be first order. So if it is going to be a second order, then the graph is going to be quadratic graph, which is second order like this. Another graph, okay, that we need to focus over here is going to be the concentration, okay, concentration against the time. Okay, we can have, okay, let's say if we are looking into a product, let's say we are looking into reactant. Yeah, so reactant, they can either reduce, okay, the concentration decrease like this. This is going to be a zero order. Now, if you have a reactant that is going to be decreasing like this, okay, this one, okay, can be either first order or it can be second order. Yeah, so there can be one like this, another one like this. Okay, so how do we identify, okay, between these two graphs, whether these two graphs, which one is going to be first order, which one is second order? If you have by using the half life, yeah, if the half-life is constant, okay, then that reaction is going to be first order. Okay, and if the half-life is going to be not the same, not constant, then it's going to be second order reaction. Okay, so this is going to be something that you need to take note. And then if you have the rate, yeah, if you have rate against concentration, then you can just use this K. So this one is going to be like this, constant, and then K first order, then you have just a straight line like this. Second order, it will follow a quadratic graph like this. Okay, so now coming back to this question, okay, if you look in a separate experiment, the rate is investigated. So you are looking into concentration versus time. So this reaction, from this reaction itself, we know that it's a curve. So it can be either first order or it can be a second order. So we don't know. So we can look at the half-life. Yeah. So here, okay, before we go into the calculation, we can see the reaction is first order. Okay, they have mentioned it's going to be first order to N2O5. It means we are looking into a constant half-life. Yeah, this can be confirmed from the graph using half-life. Explain the term half-life of the reaction. So the term of half-life in of the reaction is the time taken, okay, for the concentration of any reactant or product, okay, or the reactant, okay, to become half, okay, to become half of its original value. Now, so determine the half-life of this reaction, show the working on the graph. Yeah. So if you look at the half-life, so we know that half-life is going to be the time taken for the concentration of the reactant to become half of its original value. Yeah, concentration or volume. Yeah, to become half of it. So if you look, take at 0.25. Okay, the half of it is going to be 0.1. 0.25 divided by 2, okay, 0.12, okay, 0.125. Yeah, so if you have 0.125, should be somewhere here. Yeah, so 0.125, okay, 0.1512, 0.125. Okay, let me check. 1, 2, 3, 4, 5. Okay, 0.125. I think somewhere here. Okay, so if I bring this down, okay, I will get this value. So if I look at it, it's going to be 150. Okay, 150. And then, okay, from 0.125, okay, become half some more. Yeah, so I divide by 2. So it's going to be 0.06. So 12, okay, 5, okay, so 2, okay, so 4, 1, 0, okay, so 5, 0.0625, yeah. So 0.06, 7, 8, 9, 10, so 0.06, maybe somewhere here, yeah, 0.06, 0.7, so maybe somewhere if I just bring it over here, touch here, then come over here, 300. Okay, so you can see, okay, the time taken, okay, is constant, okay, it's being constant. So the half-life, okay, you can see this is 150, so this one is going to be 150. So every single time, okay, is constant, yeah, the time taken. So they ask you determine the half-life of the reaction. Show you're working on the graph, it's already there, yeah. So half-life, if you still want to show the working, so maybe I can just write down, okay, if it is going to be 0.25, okay, to become 0.125, okay, then the time taken is 150 seconds, okay. So from 0.125, when they change into 0.0625, then it's going to be still 150 seconds, okay. The half-life is constant. So the half-life is 150 seconds, okay. Suggest the effect of half-life, okay, of this on the suggest the effect on the half-life of this reaction if the initial concentration of N2O5 is halved, yeah. So suggest the effect, okay. So do remember, okay, if you change, okay, the half-life, if you change the concentration, okay, the half-life is not going to actually follow the concentration, yeah, because it follows the order of the reaction. So it's independent, okay, of the concentration, yeah, it's independent of the concentration. So half-life is going to be still going to be the same, yeah. So this is going to be still no change. Now, there's a formula as well, okay, that maybe will help you related to half-life. Okay, the formula is going to be, you can use the formula which is going to be T, okay, half-life equals to 0.693, which is going to be square root of 2, yeah, divided by K, yeah, so it's related to rate constant, yeah. It's a graph in 5B, so we'll use this graph. So we need to use the tangent method, yeah. So here, this is the point, okay, so you need to draw, okay, so something like this, okay, and then try to make it as okay. If you put it over there, okay, so I can roughly, if I, okay, if you, of course you can draw it nicely, okay, so if I try to calculate this, okay, this is going to be maybe here 0.1678, 0.18, okay, this is going to be 420, yep. So maybe, okay, the gradient is going to be 0.18 divided by 420, yeah. So I will bring this over here, copy. Okay, so let's calculate 0.18 divided by 420. So similar to like just now that I calculated, yeah, but you will need to show this. So it's going to be 4.29, okay, times 10 negative 4. Okay, 4.29 times 10 negative 4. So you need to show, yeah, so there should be an evidence of tangent, yeah, and then anything between 4 to 5 is accepted, okay, and then of course the unit will be still the same, yeah, because you find the tangent over here. Why we look at the tangent over here? Because rate is concentration divided by time. So this is the concentration and this is the time. Yeah, so we can straight away use the tangent. Yeah, so that is going to be the answer for this. Okay, and then okay, if you proceed further, okay, the rate equation for this reaction is shown. So they have given, okay, this is going to be again, it's a first order reaction. Okay, so nothing to do, okay, nothing to do with the other reactants and products. So you can see it is 100% depends on N2O5. Okay, so if you put over there, okay, use your answer in C1, okay, to calculate the value of rate constant. So we want to find the K value. Okay, so just now we already did, yeah, so by using this, yeah, but this one, yeah, they ask you to use this method. So we have already calculated the rate. So I'll use 4.29 times 10 negative 4, okay, and then the K value I want to calculate. Concentration is, I'm using the concentration at, okay, they say at 200 seconds, the concentration was 0.10. At 200, I'll just show you, concentration is 0.10. So I'll just use the 0.10 and you will get the K value. Okay, the K value, if you calculate, K is going to be 4.29 divided by 0.10 is 10 to the power of 10 to the power of, okay, 4.29 times 10 negative 4 divided by 1 times 10 negative 1. Okay, so you bring up, so it's going to be positive, so it's going to be negative 3. Yeah, so 4.29 times 10 negative 3. And what is the unit? Yeah, so rate, okay, is mole per dm cube per second. So you divide it with mole per dm cube over here. Okay, so you divide, you get per second. Okay, that's the unit. Now, nitrogen dioxide, okay, they react with O3 as shown. Yeah, so they give you this equation. And then the rate equation, okay, they say that it follows K, okay, NO2 and O3. It means that they mentioned that NO2 and O3, okay, they will follow the first order reaction. Now, when we do this kind of question, two-step mechanism, yeah, please remember, okay, one of the step, okay, which is the step number 1 normally, yeah, step number 1 is going to be the slower step. Yeah, so you just put slower step. The slower step, okay, must follow, okay, the order of the reaction. Like for example, if it is first order, yeah, then okay, the number of the stoichiometry must follow. Yeah, if it is 1, then it must be NO2, 1 mole. Yeah, 1 mole in front. Okay, and then it must be reacting with O3. So it must be there. Okay, these two O3, which is 1 mole, must be there in your slower step. Okay, so they are going to produce what? Okay, this one, up to you how you want to do it. Okay, so let's say, for example, when they react, okay, they are going to produce maybe if I look at it, okay, maybe I put N, okay, and let me suggest maybe I get O2 here. Okay, so maybe I get NO3. Yeah, let's actually put NO3. Okay, so I get the NO3 as my intermediate. And okay, I know the final equation don't have NO3. Yeah, so I know also I need 2 moles. Yeah, so I still, the second step, I need to make sure that I put another NO2. So when I add, I'll get 2 moles of NO2. Yeah, and no need to add O3 again because I want 1 more. Yes, already there. Okay, but do remember when I add step 1 and step 2, I need to eliminate, okay, I need to eliminate the NO3. Yeah. So how do I eliminate the NO3? I put the NO3 over here. Okay. And then when I add, the NO3 will be gone. Okay. So I am going to have, okay, I'm going to produce, okay, N2O5 over there. Okay. So this one is going to be, you're going to get the two-step reaction. So once you add these two, okay, you will get this entire equation. So when you suggest a possible two-step mechanism of this reaction, yeah, you can actually use these two reactions. Yeah. So you can see also they have mentioned about the same thing. Yeah. Now, okay, for question number 6, okay, they ask you to compare and explain relative acidities of butanoic acid, ethanol, ethanoic acid, and water. Yeah, so just now I recorded something. Yeah, so normally, okay, water is going to be our standard. Yeah, so we compare, yeah, between water, whether which one is more acidic than water, which one is going to be less acidic than water. So if you put as a standard, yeah, so you have standard, and then now I have ethanoic acid and butanoic acid, which is carboxylic acid, okay, and then I have alcohol, okay. So now I'm just comparing alcohol, okay, with water, and then also carboxylic acid first, yeah. So this is what I'm going to compare. So when I look at carboxylic acid, okay, so this is going to be C double bond O, OH, and this is going to be R. So we know, okay, before we look into R group, yeah, we know that, okay, the moment you have the O over there, okay, there is going to be what we call as, when you donate the electron, we call it positive inductive effect. Okay, when you withdraw the electron, that is going to be known as negative inductive effect. So the oxygen, okay, from here, the oxygen at the carbon double bond O, okay, they are going to withdraw the electron. So they have this negative inductive effect. Okay, negative inductive effect, where they are going to withdraw the electron from the OH bond. Okay, they will go and make the electrons to delocalize between oxygen, carbon, and O over here. Yeah, so they become delocalized. So they have tendency to form a more stable ion, which is this ion, okay, compared to the previous this carboxylic acid. So they have tendency to form this, yeah, tendency, because this is more stable. So if you have tendency to form this, it means you are going to produce a lot of H plus, yeah. So if you compare with water, of course, carboxylic acid is going to be more acidic than water, okay, more acidic than water. And if you look at alcohol, if I compare with alcohol, okay, alcohol on the other hand, okay, is ROH, okay, so they are going to give you RO minus and H plus. Okay, so what will happen here, the R is generally like, for example, ethanol and so on, that is going to be alkyl groups. Yeah, alkyl groups, okay, like CH3, C2, H5, and so on, they have positive inductive effect, where they are opposite to negative inductive effect. They are going to donate the electrons. So when they donate the electron, what will happen? Okay, the electron will come closer to oxygen, and because electron, of course, the charge, okay, this negative charge is going to become more. Yeah, so when the charge becomes more, okay, that is going to encourage the bond between negative charge and positive charge over here between hydrogen. So they have tendency to form, okay, the position is going to be shifted to the left to form the undissociated alcohol. Yeah, so they are not going to give you a lot of H plus. Yeah, so that is the reason, okay, why alcohol, okay, is going to be a weaker acid than water. Yeah, so if you recall what we have learned in the past, yeah, alcohol do react with sodium, okay, but alcohol do not react with sodium hydroxide because they do not have, okay, they don't have the acidic property, not enough acidic property until they react, like go through acid and base reaction. Yeah, so this is going to help us to predict, yeah, the position. Yeah, so you know that both of the acid, yeah, carboxylic acid is going to be a stronger acid okay, compared to water. So I just put water. The one that is going to be less acidic or the least acidic is going to be ethanol, like the alcohol. Yeah, there is only one alcohol. So now, okay, I'm just stuck with which one to put. Is it ethanoic acid or butanoic acid? So if you look at ethanoic acid, okay, C double bond O OH, okay, this is going to be, there is R group, which is CH3. And if you look at butanoic acid, okay, C double bond O OH, and this is going to be C3H7. Okay, and the difference over here, even though both of them have negative inductive effect, okay, it is attached to R groups. Okay, so the R groups, okay, for butanoic acid is larger. Yeah, it's bigger R group. A bigger R group, okay, is going to have a positive inductive effect where the electron will come in. Yeah, so do remember the electrons are going to be withdrawn over here. Yeah, so they are going to be delocalized over here. The bonds are weakened, but because of the presence of this alkyl group, yeah, so some sort of a donating of the electron will some sort of stabilize this particular bond better. Yeah, because rather than all the electron go there, they will push, yeah, towards there. So that will actually some sort of strengthen the OH bond. Okay. Alternatively, if you look at this CH3, they are small. Yeah, small R group. They are not going to strengthen that OH bond better. Yeah. So in this case, okay, the one that will strengthen the bond, okay, will make sure, okay, that the H plus don't come out. Yeah, so if you look over here, they don't strengthen the OH bond, so it means more H plus will come out. Yeah, so the CH3 C double bond O minus will be formed. Okay, but in this case, okay, they are not going to encourage the H plus to come out. Yeah, because more bigger R group. Yeah, so that is going to make the ethanoic acid to become most acidic compared to butanoic acid. So if you want to compare and explain, compare already done, okay, explain, you do not need to mention so much about water. You just need to mention about ethanol. Okay, ethanol, okay, they are going to actually, when they dissolve in water, they are going to give you this equation. And then you can say because of the presence of the R group, okay, they are going to have a positive inductive effect, yeah, where they are going to donate the electron towards the OH bond, yeah, and this will stabilize this ethoxide ion. We call it ethoxide ion. So this ethoxide ion is going to be stabilized, okay, and then they are going to gain, not to say to stabilize, the negative charge is going to become more, yeah, and they are going to react with the more H plus, where the position of the equilibrium will be shifted to the left. Yeah, in that process, okay, the H plus is not going to be released as much as possible. So the OH bond is not going to be that weak. Yeah, so you explain that. So that is the part that you can see over here when I in the marking key. Positive inductive effect, electron donating effect. So you just mentioned about that. So that one is done. Then nothing to do with water. You won't even find about water over here. Yeah. So the next part is going to be, you put them together. Yeah. Carboxylic acid. Then you talk about the negative inductive effect. So you see the negative inductive effect. So it means they are talking about the C double bond O, yeah, where they are going to withdraw the electron and make it stabilize over here. Yeah, so they are going to have this negative charge delocalized between oxygen, carbon, and oxygen. So they are going to make, okay, that this particular ion to be stable. So they are going to make the reaction to move more towards to the right. So it means more H plus will be provided. So you are going to have a stronger acidity compared to water. So for both of them. And lastly, okay, you compare ethanoic acid and butanoic acid. So you compare between these two R groups, which is going to be, you tell, yeah, butanoic acid, they selected the C3, yeah. So they selected this butanoic acid. They say that, okay, this one will have a positive inductive effect where they donate the electron, yeah. When they donate the electron, what will happen? Okay, the bond between the O and H is going to become stronger. Okay, difficult to be broken. So you can actually mention about that. So you can see all the key points that is being used, okay, in order to get these 4 marks. Yeah. So I'll move on. Okay, so 3 carboxylic acids, okay, methanoic acid and ethane dioic acid, I have put over there because according to our syllabus, okay, under carboxylic acid, we have learned methanoic acid and ethane dioic acid can be oxidized. Yeah, can be oxidized. In fact, methanoic acid can be oxidized with even the phthalate, yeah, and toluene, the weaker oxidizing agent also can, yeah. Potassium manganate, potassium dichromate, yeah, can. So ethane dioic acid on the other hand, it can be only oxidized by stronger oxidizing agent. So cannot with phthalate and toluene, yeah. So maybe some information before we continue. And then we have butane dioic acid. Now this one, butane dioic acid, yeah, we don't get, they cannot be oxidized. So 2 tests were carried out, a separate sample on this organic acid as shown, yeah. So they say that, okay, methanoic acid, okay, can undergo something, okay, but the ethane dioic acid and then the butane dioic acid cannot go through that, okay. So and then they say that, okay, this ethane dioic acid, okay, they can actually undergo the same reaction with methanoic acid, yeah, but the other butane dioic acid cannot go through, yeah. So this one, I think we already put the points over here, yeah. The only thing that can react, yeah, with methanoic acid only is going to be the oxidation involving phthalate and toluene, yeah. So you can choose, okay, which one you want to use over here. So let's say if you use phthalate, yeah, phthalate solution, yeah. So phthalate solution, so what is going to be the condition? Yeah, the condition is going to be you need to either phthalate or toluene, you need to warm the mixture, yeah. So you need to warm. Okay, so what will happen? The phthalate solution, okay, it is going to give you a brick red precipitate. Okay, so brick red precipitate. So if you use the, okay, if you use the toluene, okay, then you are going to get the silver mirror formation. Precipitate, okay, or PPT. Now, if you use toluene region, then you are going to get the silver mirror observation. So up to you which one you want to use, yeah. But now, you see both of them can react. If both of them can react, then you have to choose, the acidified potassium manganate, yeah. So acidified, acidified, the stronger one, yeah, acidified KMnO4, and then you warm, acidified potassium manganate, and then what is your observation? It's going to decolorizes the purple, purple color become decolorized, becomes decolorized, and because they are going to form carbon dioxide, and water, so carbon dioxide, they might appear as bubbles, so they do accept bubbles also, so do remember, in order to get the marks, you need to mention, the conditions, complete the table, observe change, assume this one all have similar acid strength, done, Now, each of the compound, so you have methanoic acid, ethane dioic acid, butane dioic acid, is dissolved separately in CdCl3, So CdCl3, is going to be the solvent, and you can, they say that after that, they use the proton NMR and carbon-13 NMR, proton NMR and carbon-13 NMR, so they ask, if you use, this, how many number of peaks, that can be obtained, in proton NMR, how many number of peaks, in carbon-13 NMR, so we need to find out, so this one, they are using CdCl3, so they are not using D2O, Yeah, so nothing will disappear. Yeah, so CdCl3 only. Okay, so now, okay, let's actually look at the NMR first. Okay, so H C double bond O O H. Okay, you can see, okay, this is going to be one environment, and this is going to be another environment. Okay, therefore there should be two peaks over here. Okay, let's look at carbon 13. Yeah, there is only one carbon, so of course one. Okay, so I'll just put only one peak. And let's actually go on for, okay, C double bond O OH, double bond O OH. So you can see here, okay, this environment, okay, is the same as this environment. Okay, they are going to be the same. So there is only one peak in the NMR. Yeah, so you just need to figure out that. Yeah, and then the number of the carbon 13. Yeah, carbon 13 NMR. You see, this environment, okay, is attached to C double bond O, and then OH. Yeah, then the COH. Yeah, it's the same as this environment. Okay, they are the same. So still one. Okay, and lastly, okay, 4 carbon. So 1, 2, 3, 4, double bond OOH, double bond OOH, H. Okay, let's actually try for proton NMR. Okay, proton NMR, I know this and this are the same. Okay, so 1. And this must be the same as this. Okay, but do remember, if I write down, hydrogen is attached to carbon, that is attached to hydrogen, that is attached to COOH, and that is attached to CH2COOH. Okay, let's have a look at this hydrogen. Okay, must be the same as this. So let's see whether they are the same or not. Hydrogen attached to carbon, that is bonded, okay, the hydrogen bonded to another hydrogen. Yeah, then it is also bonded to COOH, and it is also bonded to CH2COOH. So you see, same. So it means that, okay, I can simplify that this, and this are the same environment. Okay, so how many hydrogen environment? There are total 2. Yeah, 2. Number of carbon 13 NMR. Okay, so if I look at carbon 13 NMR, this is the same as this. Okay, and this, okay, CH2 and then COH, CH2, so must be the same as this. Okay, so there are 2. Okay, blue and purple. Okay, or pink, blue and pink. So 2, 2. So you can see all the same, and then now, so now the proton NMR spectrum of this, yeah, in D2O. Now, yeah, there are certain things that will disappear. Yeah, so I'll just bring this here. Okay, so what are the things that will disappear over here? Okay, of course, the one that will disappear is going to be the one involving this. Yeah, the OH. Yeah, so the OH will disappear. So explain the difference. Okay, previously, okay, we supposed to have 2 peaks. Yeah, so now you are only going to have 1 peak. So only, okay, 1 peak will be observed. Okay, the OH peak will disappear. Okay, will disappear because of rapid exchange with D2O with even mass of hydrogen, which will not give spectrum. Okay, okay. So that is going to be 1. Okay. I think that's the only one difference. Yeah. So you can see, okay, OH disappears, proton exchanges with deuterium. Yeah. So because rapid exchange, okay, of proton. Okay. So maybe you can add a proton. Okay, with the D2O or the D, yeah, deuterium. Okay, but we cannot see, okay, because of the even mass of the hydrogen. Okay, even mass of hydrogen, which is hydrogen 2. Okay, so you explain using that. Okay, that is 1 mark. Okay, so let's actually move on to C. So 1,4-dibromobutane, okay, is used in the synthesis of dicarboxylic acid J and diamine of K. So they have already given all this information. So they are going to tell us, yeah, they are going to have few steps. Okay, step number 1. Okay, when I look at this, okay, you are producing carboxylic acid. Okay, so let's actually look at the number of carbon. Yeah, 1, 2, 3, 4. Okay, 1, 2, 3, 4. There is no need to add the number of carbon. Yeah, so number of carbon is all good. Okay, so no problem. Okay, so what you need to do, okay, is to change this halogen alkane, yeah, the Br, into something, okay, that can be changed into carboxylic acid. Yeah, the only thing that I can think of is you change it into alcohol. Okay, so if you change this one into OH group, the Br and OH group over here, each of them, okay, you look at CH2, then OH, then they will become R. Okay, the same thing the other side. So they are going to follow the primary alcohol. Yeah. So if primary alcohol, okay, primary alcohol, they can be oxidized to become aldehyde, then further oxidized to become carboxylic acid. So now, okay, I know what will happen over here. So I just need to do oxidation. So what I need to do in step number 1, yeah, step number 1, I need to change, yeah, the halogen alkane with OH. So this one is going to be nucleophilic substitution reaction. So you react with NaOH. Okay, so this one you do not use ethanolic condition, so it's just NaOH. Okay, because if you use ethanolic condition, then you are going to have elimination reaction. So we don't want that. So sodium hydroxide. Okay, then this one should be, if I'm not mistaken, heated under reflux. Yeah, or warm. Okay, so that is going to be, okay, so you see here heat. Yeah, so NaOH you heat, okay, you are going to get, okay, so I'll just write down OH, CH2, 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 OH. Okay, so draw the structures, okay, of G and H in boxes. Yeah, so I draw the structure. So in this case, they didn't specify, yeah, what kind of structure should I draw. I'll just write down the structure formula still. Okay, yeah, no need to draw, yeah, display formula. What if they want you to write down, then they will be specific. Yeah, so in this case, it's okay. Yeah, then after that, you do oxidation. Oxidation, okay, of alcohol, okay, you can use acidified KMnO4, okay, and then you heat under reflux, okay, so this one, okay, or warm, yeah, so you can have that. Okay, later if they ask, we can include. So now, okay, let's actually look at formation of amine. So again, okay, let's look at the number of carbon. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. The moment you see, okay, the increase in number of carbon, okay, you know for sure react with KCN. Yeah, so you need to react with KCN, okay, and you react with KCN, okay, you need to make sure that you react with heat, okay, and then this one KCN must be with ethanolic condition. Yeah. So ethanolic with ethanol, heat and with ethanol. Okay. So you are going to have, okay, the Br will be replaced by Cn. So this is nucleophilic substitution. So I know, okay, CH2, 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 CH2. The Br will change it to Cn, okay, and the Br over here will change it to Cn. Okay, so this is going to be the H. And how do you change nitrile, okay, to become amine? This is nitrile, okay. How do you change into amine? Okay, so this one, okay, they are you need to do reduction. Okay, so this reduction nitrile to amine, you can use 3 methods, but I told you out of these 3 methods, one of it has been removed from the syllabus. Yeah, so you can use LiAlH4 in dry ether, okay, and or heat in dry ether. Yeah, so the or you can use react with hydrogen, okay, and use platinum, okay, as the catalyst, or okay, last time, okay, you can use ethanol with sodium. Yeah, but now it has been removed from the syllabus. I will not look into that. Okay, so you are going to get, okay, the nitrile, you are going to get, okay, the H coming in, okay, and then you will have the K. Yeah, so now draw the structures. I have already drawn. Suggest region and condition for step number 1. Okay, number 1, you use NaOH aqueous, okay, condition heated under reflux. Okay, in the marking key they say heat, okay, heat under reflux. Okay, they are not going to deduct marks from you. Yeah, heat is already okay. Yeah, so if you want to say heat or heat under reflux, yeah, up to you. Yeah, just put, okay, if you're not sure. Yeah, so heated under reflux. And then, okay, step number 2, okay, is going to be oxidation reaction. So you react with KMnO4 acidified, okay, acidified KMnO4, okay, acidified KMnO4, okay. Then, okay, make sure it's also heated under reflux or warm, okay. So you can see, you can always check. Yeah, you can also use acidified potassium dichromate. Yeah, if you have the marking key with you, you can check. Okay, step number 3. Okay, of course you need to react with KCN. Yeah, but make sure KCN, okay, it is going to be ethanolic. Okay, I don't, they didn't write down ethanolic over here. I will write down. Yeah, KCN, okay, must be ethanolic. Okay, and then, okay, must be heated. Okay, must be heated. Step number 4, okay, is going to be, you can either use this or this. I'm going to use LiAlH4, okay, okay, in dry ether and heat. Okay, but here they say allow Na in ethanol, not in your syllabus anymore. Okay, I didn't see that in your syllabus anymore. Yeah, sodium in ethanol. Yeah, or you can just use hydrogen with nickel, platinum, palladium. Yeah, so in your syllabus they say nickel and platinum. Okay, up to you. Yeah, so which one you want to use? Okay, but I've already written. Now let's move on. Okay, polyamide L. Yeah, so polyamide L. Okay, they can be synthesized from this. Yeah. So they have given you all this. Draw the repeat unit, okay, of the polymer form, okay, in the box. Okay, so you just need to draw the repeat unit. Okay, the repeat unit. So you can just no need to put bracket and n, just a repeat unit. So here, okay, I will, maybe I'll just put nitrogen, hydrogen, hydrogen, CH2. I put 6, and H2. You react with C double bond O OH, then CH2 to C double bond O OH. Okay, so the H from here, OH from here. So of course OH from here, H from here. Okay, so when you draw, okay, I'll just straight away draw here, nitrogen, hydrogen, leave it like this, yeah, and then CH2 bracket 6 NH, okay, and then join with carbon. The moment you see this, bring the double bond O like this, yeah, and then you join CH2 to C double bond O like this. Okay, this is going to be how you draw. Yeah, so they say draw the lipid and then the functional group should be shown, displayed, and so on. If you want, yeah. Also, just okay, say that this is going to be the peptide linkage. If you want to show, yeah. Now, so if you move on, okay, question number 7, okay, 3 amino benzoic acid, okay, is going to be synthesized from methyl benzene in 3 steps. Yeah, so you have methyl benzene, and you are going to end up, okay, in getting benzoic acid. So it's okay here. The moment I see benzoic acid, yeah, I know. Okay, I at one point of time, okay, I can just oxidize, okay, the methyl benzene. Okay, but do remember the oxidation of methyl benzene is going to be slightly different than the normal oxidation because I will use potassium manganate. Okay, but it must be in alkaline solution. Then you add, okay, into acidic, you add acid, yeah, dilute acid. So first alkaline solution, then you add acid. This is slightly different, yeah. So heat under reflux, okay, or heated or warm, yeah, up to you, yeah. So I'm just going to maintain heat under reflux, yeah. So I know one of the point. I don't know when, okay. So I just put, yeah. And then there is one point of the reaction, yeah, maybe step 2, maybe step 1, yeah. I do notice that I have this NH2, yeah. But okay, you need to be very careful, yeah, because the position that NH2 is coming in is at position number 1, number 2, number 3. Okay, so it must be a group that is position 3 directing. Okay, if I want to actually have the NH2 directly, yeah, if I want to have the NH2 directly, I cannot add them directly. Okay, like the NO2 will come over there first. Yeah, I cannot actually just add directly because methyl is going to be position 2, 4, 6 directing. Okay, so it means that first of all, okay, this is giving me idea that first I need to change it into benzoic acid first. And benzoic acid is the one, this COOH group is the one that will be position 1, 3, 5 directing. So that is the only way. After that only, after you put the benzoic acid, you can react, okay, before you get this NH2, then you need to do the nitration. Okay, so when you put the nitration, the benzoic acid, okay, they will actually will direct the NO2 group into position number 3. Okay, so you will get the NO2 in position number 3. Then from NO2, you can actually get the NH2. Okay, so that is how you do the reaction. Yeah, so draw the structures of M and N in the boxes and suggest regions. So now I know what to do already. Yeah, so I will put, okay, this one is methyl benzene. Okay, I put the methyl benzene. Okay, CH3. Okay, and then there will be at this position, okay, because it's 2, 4, 6. Yeah. So this one, okay, sorry. Okay, this one is going to be, I am going to change this into carboxylic acid straight. Okay, so it means that, okay, this will come at step number 1. Okay, So I get this. Okay, after that, my step number 2 is the nitration. Okay, so I will actually have the benzoic acid, and then I will have the NO2 here. Okay, so step number 2, okay, it must be reacting with HNO3, okay, with 55 degrees Celsius. Okay, nitrating mixture. So you must also have H2SO4, concentrated. Yeah. And then, okay, after nitration, okay, that is step number 3. Okay, step number 3, okay, is going to be you are going to react, okay, with SN with dilute HCl. I hope you remember all this. Okay, you are going to get, okay, NH2 amine over there. Yeah. So draw the structures. Okay, it's done. Okay, you can see also. I think they already draw also. Okay, done. Then, okay, suggest region for number 1. Okay, so number 1, they want regions and conditions. So make sure, yeah. So number 1 is going to be step number 1, hot, okay, KMNO4. Okay, but okay, they didn't say, they didn't give you more information. Alkaline first, okay, then acid D5. Okay, I will add extra. And then, okay, for the step number 2, okay, concentrated H2SO4, okay, and concentrated HNO3 at 55 degrees Celsius. They didn't mention also. Yeah. And lastly, step number 3 is going to be SN, okay, with concentrated HCl. Yeah, I think this one maybe I'm wrong. It's not dilute, it's concentrated. So concentrated HCl, okay, and then you heat. Okay, so these are the conditions. Okay. Next, a mixture, okay, of this serine and lysine. Okay. They react to form several different products. Okay, draw the structure of 2 structural isomer, okay, with the molecular formula of this, okay, that can be present in the product mixture. The functional group formed in each case must be displayed. Yeah, so a mixture reacts to form different products. Okay, so they form different products, and then you need to draw structure of 2 structural isomers. Okay, let's actually form the product. Okay, let's see, C6H12N2O5. Yeah, I think maybe we just draw, okay, this one first. Okay, C6, let me check. Yeah, so 1, 2, 3, 3, 4, 5. Okay, 5 plus 4 is 9. Yeah. So I don't think so it's direct. Yeah. So they say draw the structures of 2 isomers with the molecular formula C6H12N2O5. And that could be present in product mixture. Mixture of serine reacts. Okay, let me try first. Okay, so you have CH2, CH, NH2, COOH, and then OH, CH2, 4, CH, NH2, COOH, and then So now, okay, when I look at it, okay, I know that if I want to get 6 carbon, yeah, there is no way that I can join them together. Yeah, don't do that. Yeah, so even when I look at it, yeah, if I just join them together, okay, and form a typical polyamide, I will get number of carbon is more. Yeah, so what I can see over here is the trick is they say C6, right? Okay, they say C6. It means that 3 carbon, then 3 carbon with 3 carbon. So it means that this one, okay, I just need to make double of this. Okay, you see, I'll make double of this. And when these two reacts, okay, they say mixture of product, right? When these two reacts, then I can have possibilities of having 6 carbon. Okay, so I am going to ignore this one. I'm not going to react with that. Yeah. So I need to just rearrange a bit. Yeah. So I just need to put the NH2 properly. Yeah. So C. Okay. Let's say I put the C double bond OOH over here. So maybe the NH2 I put here. Okay. This one and this one. So I have, okay, I have H. Okay. And I have CH2OH. Okay, so this is going to be my plan. Yeah, my plan. So I want to actually react with this. Okay, but I need to check also the oxygen must be 5. Yeah. So if I check, okay, when I join together, okay, let's say with another molecule of this, okay, I must check that I'm going to get the same. Yeah, the same as this. Okay, so if I do that, okay, let's say the hydrogen and this one will go out. Okay, so I am going to get, okay, I will erase this. So I get NH2, CH, CH2OH, C double bond O, and H, C, CH2OH, H, COOH. Okay, so if I count, yeah, so I must have 6 carbon. I have 6 carbon. Okay, so almost correct. Okay, hydrogen, okay, I must have 12. Yeah, so if I count 2, okay, 4, 6, 7, 8, 9, 10, 11, 12. I have 12. Nitrogen, I have 2. Yes, I do have 2. Oxygen, I have 5. Yes. Yeah. So they say that, okay, draw the structural structures of 2 structural isomer with this. Okay, this is one of the structure. Yeah, one of the structure. So I will just bring this, copy and paste. Okay, so they want 2 structural isomers, okay, with the molecular formula. So this one, I need to change the structure. Okay, I change the structure. Okay, from when I see the marquee key, yeah, I can see that they use the OH here up, NH2. Okay, they just use the same thing, okay, but they use basically they didn't redraw this polymer. Yeah, so it means that they are going to use this and then try to come up with another isomer, okay, that will share the same molecular formula. So here, when I look at this, okay, what is another isomer that I can have? I think this one, I think we have to draw another one. Yeah, so I think that is the best way also. Hold on. Okay, if you draw another one, okay, so this one, okay, I'm reacting carboxylic acid and amine. Okay, so what else we can do? Okay, we can actually react carboxylic acid and alcohol. Okay, so let's actually draw, okay, CH. So I put C double bond O, OH. Okay, and then NH2 I bring here. And then the alcohol, okay, CH2 OH, I put it here. Okay, so now I copy this, paste, this. These two reacts, okay, you can see the OH and H, okay, will come up. Okay, so you are going to get OH, CH2, CH and H2, C double bond O, O, CH2, CH and H2, C double bond O, H. Of course, it's going to be the same as this, H2O, H2O, so no need to calculate this again. It's going to be the same. Okay, so this is the answer. This is another one that they want. Okay, this one have to think a bit. Okay, so just need to think more. Okay, done. They didn't specify that you need to write in what form, yeah. So they say the functional group form in each case should be displayed. So we already displayed that. Okay, the functional group that is being formed here is going to be this one. And the functional group that is being formed here is this one. Now, predict the number of different structural isomer with this, okay, that could be present in the product mixture. Yeah, so they are asking us to predict, okay, for C9. Yeah, C9 is going to be basically you are going to draw for this. Yeah, so if I am looking at it, okay, there is going to be NH2, NH2, COOH. Yeah, so there are two NH2, okay, and COOH. So you are going to get, okay, if you use the NH2 and COH, then you are going to get two types, okay, two types of, okay, if I combine, I am going to get carboxylic acid and then amine, okay, then it's going to be, you will get one polyamide, okay. And if I join with this, okay, I will get another polyamide, okay, number of structural formula. Okay, so 2, okay, but why 4? Okay, this one have to really predict different structural isomer. Yeah, C9, H19, and 3O4. So there are 3 nitrogen. Yeah, 3 nitrogen, this one and this one. Nitrogen. Okay, this one I think we will actually come back again. Yeah, so this one definitely have to draw. So I know at least 2. Yeah, because the carboxylic acid group. Okay, and then you are going to have C9. So 4, 5, 6. This is 3. Oh, okay. So it's like this. Okay. If you predict, okay, we know that there are 2 groups over here, okay, of NH2 and NH2. So here you are going to get 2. You are going to get 2 types, okay, 2 types of polymer, okay, 2 types of polymer. And then if you join the polymer with this, okay, this is within, yeah, within. If you join with this, because of the presence of this and also CO2H, yeah, you are going to have another 2 types over here. Yeah, so this is going to actually give you the total of 4 structural isomer. Okay, because it's C9. So within itself, okay, double of this, or okay, you are going to join with this and this, yeah, so 2 and 2, so total 4. Okay, now next question. Is it okay for Ewan? Frederick? Anything you want to me to explain?
Can you explain that part again, sir?
Okay, so you see here, okay, remember just now, okay, we get 2 types over here, right? Okay, 2 types of isomer, yeah, from just this serine alone, yeah. So serine and serine, you join together, you get 2 types, yeah. Now, here, okay, you are going to actually look at C9, yeah, C9. It's going to be similar like just now, yeah. C9 means carbon is going to be 9. So you see here, the carbon, okay, there are going to be 4 carbon here, 5, 6 carbon over here, yeah. So 4, 5, 6 carbon over here, okay. So if you have 6 carbon over here, if it is going to be C9, okay, it means that, okay, it must react, okay, with this. Okay, it must react with this. Okay, so when they react, okay, you can react, okay, with COOH, okay, with the NH2. Okay, you get 1 product. Okay, and then you can also react, okay, COOH can also react with OH. You get another product. Okay, so you have 2. Okay, and then, okay, are you still with me, Frederick?
Yeah.
This one react 1. You react with this, you get 1. Okay, so already 2. And then you look at this NH2. When this NH2, okay, they react with this. Okay, you get another one. Okay, another one. And okay, when this NH2 react with this COOH, you get another one. Okay. And then, okay, we know that, wait, one more. NH2COOH. So 4, and there's 4. Yeah, that's all. Yeah, I think that's all. Yeah. So that is the 4. Okay, I thought it's 6. Yeah. So this one, okay, they are going to be 4. Okay, Frederick. So you see, because of the presence of 2 NH2, so you are going to have 1, 2, 3, 4. Is that okay, Frederick?
Yes, sir. Thank
Yeah,
you.
if you draw, then it's going to be more complicated. But this one, we just need to predict only. Yeah. So there is going to be 1 amide over here, 1 amide over here. Okay. Another amide over here, another amide over here. Yeah. So something like that. So there are 4. Yeah. Done. Now 3 more minutes. Okay. Now this is going to be naturally occurring compound. Okay, found in plants. Okay, on this in this compound, okay, label each chiral center. Yeah, so this one, you see, chiral center means must have 4 different groups. Yeah, no, okay, no, okay, so I'm just no. Okay, so if I have this, okay, I know this is a different group, and this is different group, that is hydrogen. So this is going to be a chiral center. Okay, this one cannot. 2 hydrogen. Hydrogen cannot. Okay, 3 bonds only, cannot. Okay, nitrogen 3 bonds only. Okay, cannot. Okay, so now here, different, hydrogen different, this is different, this is different. So chiral center. Okay, the one that cannot, I'm going to erase first, yeah, so that we can see. Okay, this is cannot. Okay, 2 hydrogen. This one 3 bonds only, cannot. Of course, cannot. 2 hydrogen, cannot. Okay, hydrogen here, cannot. 3 bonds only, cannot. Okay, so how many? Okay, if I erase the part that cannot, okay, there are only 2. Okay, there are only 2. Yeah, you can see. Okay, from the answer key also. Okay, so draw the structure of 3 products formed, okay, after complete acid hydrolysis, okay, of glutathione, this compound, yeah. So assume, okay, the thiol group do not react. Okay, so 3 products, okay, acid hydrolysis, yeah. When you do acid hydrolysis, the bonds that are going to be broken, okay, is going to be the bond between here. Okay, the amide bond will be broken. Okay, and you can see there is another amide bond here. Okay, so they are total only that, yeah, only that. So you are going to draw 3 structure. Okay, so you just put the OH here, double bond O, then NH2, then like this, double bond O, then OH. Okay, so that is going to be carboxylic acid. And then here, NH2. Okay, so NH2. You can just write down NH2. NH2, go like this, go up, then go up, SH. Then here, double bond O. Then you are going to have, okay, the OH. Okay, that is going to be that part. And then this one is NH. Okay, this is going to be NH2. So straight away, I write down NH2. And then join here, double bond O, OH. Okay, so you are going to have, okay, total of 3 products. Okay, you can just double check whether it's correct or not. Yeah, so it should be correct. Okay, by referring, okay, to this structure, okay, explain why it is soluble in water. When something is soluble in water, it means they can form hydrogen bonding, yeah, with water molecules. And you can see the one that can form hydrogen bonding with water, yeah, carboxylic acid can form hydrogen bonding, NH2 can form hydrogen bonding. So you can see here, okay, identifying, okay, here, part 3. C3. Okay, they didn't give the answer over here. Yeah. So here, okay, by referring to the structure, okay, explain why it's soluble in water. It is capable to form hydrogen bonding. Okay. Okay, with water, okay, using COOH group. Okay, carboxylic acid is soluble. Okay, amine, yeah, amine. Okay, they can also form hydrogen bonding. Yeah, so you just take note of that. So they ask, okay, this question: this substance, okay, is soluble in water. By using the structure of this structure, explain why it is soluble in water. So if you look at this structure, okay, there are a few things that we can notice, which is going to be the carboxylic acid group, okay, amine, okay, carboxylic acid group, okay, and then the presence of this NH, okay, and also the O. Okay, all these, okay, are able to form hydrogen bonding, except with NH2. Normally, if you have a complex amine, okay, normally they are not soluble in water, but all of them, okay, are capable to form, okay, the hydrogen bonding with water. So you can actually write down, okay, hydrogen bonding, okay, can be hydrogen bonding can happen between COOH group, amine group, nitrogen and the nitrogen atom and oxygen atom. Nitrogen and oxygen atom. Might or peptide linkage. Water. Making it soluble in water. Making glutathione soluble in water. So the next part is going to be this one. If you look at this graph, this one has been removed. pH graph has been removed to AF. No longer in A2. But again, there are total 4 marks. So we try to answer this. This one, I have already taught you. So you still need to know how to answer these kind of questions. So let's say, we assume that you know all this. So in the region circle on the graph, identify 2 organic species that are present in the solution. So we are adding sodium hydroxide. So inside, the titration is going to be ethanoic acid. So the pH is measured from the ethanoic acid, which is in the beaker. So ethanoic acid must be there. As the sodium hydroxide is being added, then the pH is going up. So you are going to write the equation. The equation, if you write down ethanoic acid reacting with sodium hydroxide, you are going to get salt and water. So the sodium ethanoate is being formed. So here, we know that, as sodium hydroxide is being added, they are completely reacting. So as it is being added, this is going to be in excess. You are going to get 2 types of organic molecule over there, organic compound, which is this ethanoic acid and sodium ethanoate. So that is going to be the 2 species that is going to be present over there. Ethanoic acid, and then you are going to have CH3COO minus and A plus. So this is identifying the 2 organic species. If you want to give name, then you write down ethanoic acid and sodium ethanoate. And we know that the presence of this ethanoic acid and the salt of the ethanoic acid, ethanoic acid is a weak acid, and the salt of the weak acid is going to form a buffer solution. And they say that the mixture is going to be, the pH is going to be changing slowly and gradually. So the reason why the pH is changing slowly or gradually is because both of the species behave as buffer, behaves as buffer, where small addition of OH minus does not change the pH significantly. So you just need to also identify that this is going to be as a buffer solution. So you need to tell also what actually happens. We know that CH3COOH is going to give you CH3COO minus plus H plus, and then this is going to be, you are going to get completely CH3COO minus and Na plus. So this is going to be the equation. So when you add the OH minus, the OH minus is going to react, react with H plus. So the position of the equilibrium, shifted or shift to the right. Shifted to the right. To remove the OH minus. So the increase of CH3COO minus, is going to be compensated by the large reserve, of ethanoic ion, okay, in the salt solution. Yeah, so it is going to be, you can include all this together. Okay. Now, the equivalence point in this acid-base titration is where two solutions have been mixed in exactly equal molar proportion. So explain why pH is greater than 7. So basically, this is going to be carboxylic acid, which is weak acid, and sodium hydroxide, which is going to be a strong base. Okay, so it is going to be a weak acid plus strong base titration. Okay, so this will result in equivalence point which is greater than 7. Okay, but if you want to explain further, okay, do remember, okay, as you react, okay, you are going to form, okay, this CH3COO minus Na, okay, and then there is water. Okay, do remember that, okay, CH3COO minus or COO minus Na plus, they can react, okay, with water, okay, to give you they can react with water, okay, to give you CH3COOH, okay, and then NaOH, okay, because water also, okay, they can give you H plus and OH minus. So in that case, yeah, this is going to give you, okay, the presence of OH minus, a lot of OH minus over there. Okay, they are going to increase the pH, which is going to be greater than 7. Okay, that is going to be one of the reasons, okay, why, okay, you are going to get the pH which is greater than 7, yeah, the equivalence point. Okay, so at equivalence point, okay, you do have this ethanoic ion. This ethanoic ion, they are going to react with water, okay, where they are going to give you sodium hydroxide, which is going to produce OH minus. Okay, so this presence of extra OH minus over there, okay, is going to give you the basic property, yeah, which is going to be pH slightly greater than 7. Yeah. Now, impure sample of vanadium vanadate, yeah, with the mass, okay, is dissolved, and then they say in this equation, all the vanadium from here, okay, they exist in this form. Okay, and then they say that you need to filter to remove any zinc powder. Then after that, when the resulting solution is titrated, yeah, so you are going to use all this information. Okay, they are going to oxidize V2 plus ions back to VO2 plus ion. Okay, so we need to calculate the percentage. So here, okay, I know that, okay, I'm going to use MnO4 minus plus 8H plus 5 electron to give me Mn2 plus 4 H2O. I'm going to use this equation to change V2 plus. Yeah, so V2 plus, okay, plus 2 H2O. I just change the position. So you are going to get VO2 plus 4H plus 3 electron. So if I want to use this equation, if I want to combine them together, okay, I need to actually eliminate the electron. So this one I times by 5, yeah, to get 15. This one I times by 3. So everything, yeah, the entire equation. So times by 3, okay, this one 8 times 3 is going to be, okay, let me put over here, 8 times 3 is going to be 24. Okay, then 15. So this one is 3. Okay, this is 12. And then times by 5. Okay, so this is going to be 5. Okay, then 10. And then this is 5. Okay, so 5 times 4, 20. And then 15, yeah. So when I add this together, okay, I am going to eliminate the electrons, okay, the 15 electrons. So I'm going to get 3 MnO4 minus, okay, plus 24H plus, I just write down first, yeah, everything. Okay, later you still need to simplify further. Okay, now you look at the part that is some sort of similar, yeah. So you see 10 H2O with 12 H2O, I can bring to my right hand side. I am going to have, okay, this one cancel, okay, minus 10, so I'm going to get, okay, 2 H2O, okay, 2 H2O there. And then, okay, I can also look at my H plus. Okay, when I bring this H plus to my left, okay, I can cancel this. Okay, so this one minus 20, so I will have 4 H plus. Okay, so if I rewrite everything again, 3 MnO4 minus, okay, plus 4 H plus 5 V2 plus, it's going to give me 5 PO2 plus 3 Mn2 plus, okay, plus 2 H2O, done, yeah. So this is going to be, okay, the equation, yeah, for the converting this V2 plus, okay, to become VO2 plus, yeah. So here, okay, I have the information that I can use, which is going to be, I can determine the number of moles, okay. So 20.1 times 0.025 divided by 1000, you will get the number of moles of MnO4. Okay, if you calculate that, yeah, you are going to get, okay, 5.025 times 10 negative 4. Okay, that is going to be the number of moles. Okay, so do remember this 5.025 times 10 negative 4 is for 3 moles. So now I need to calculate, okay, I need to work my way up to calculate what is this, yeah. So this is going to be 5 moles, this is 3 moles. So what I can do is 5.025 times 10 negative 4 divide by 3 times by 5. Okay, that is going to give me the number of moles of this. So if you calculate that, you are going to get, okay, I have calculated that part just now, yeah. So you are going to get 8.375 times 10 negative 4. Now, what do we have over here? Okay, you generally have, okay, they have mentioned that, okay, all vanadium present is going to be VO2 plus ion. It means everything that you have over here is going to be over there, which is going to be as simple as, okay, number of moles, okay, number of moles of NH4VO3, okay, is the same as the number of moles of VO2 plus ion. This is very important. Okay, that is going to be, everything is going to be present in that part. So it means that I can find out, okay, what is going to be the number of moles of this, okay, which is the same, which is 8.375, okay, times 10 negative 4. So left with, okay, calculating the mass, yeah. So if you want to calculate the mass, okay, of this number of moles, we know, yeah. So how do we calculate the mass? The mass is going to be number of moles times the MR. So number of moles is going to be 8.375 times 10 negative 4. Okay, the MR, okay, you can calculate, okay, which is going to be nitrogen is 14, yeah, hydrogen is 1, so times 4. Okay, vanadium, if you go and look at your periodic table, you are going to get 50.9, yeah, 50.9, okay, plus, okay, 3 times 16. So if you calculate this, okay, you are going to get, okay, if you calculate, you are going to get 0.0979035, okay, 0375 gram. Okay, this is going to be the gram that exists in this molecule, that compound. So we know that, okay, the mass is 0.15. We need to find out what is going to be percentage by mass. Okay, so if you want to calculate the percentage of mass, okay, you just need to take the value, the mass that we have just now, yeah, then divided by 0.15, okay, and you times by 100%, and you will get, okay, in 3 significant figures, you will get 65.3%. This is what we need to write down, yeah, 65.3%. Okay, the next part, okay, the next question, okay, is going to be, this is the last question. Okay, normally they have 10 questions, but now they have 9 questions. But this question, they give 6 marks. Okay, so they just want, okay, you to identify the structure. That's it. I think just draw the structure. So when they say draw the structure, you can draw in skeletal formula, displayed formula, up to you. Yeah. But okay, when I look at this question, okay, what we can see, okay, the moment you see there's a lot of carbon, okay, so 8 carbon, okay, normally when you have 8 carbon, okay, if you have a straight chain or something like this, okay, if it is 8 carbon roughly, yeah, we are dealing with, okay, 1, 2, 3, 4, 5, 6, 7, 8. We might be dealing with, okay, a lot of hydrogen. Yeah. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18. Okay, but here you are going to have only 8 hydrogen. So how do we have a lot of carbon but less hydrogen? Most probably this is going to be dealing with something that has, okay, a benzene ring. That is the first thing that we can put over there. Okay, so if you have a benzene ring, that's already C6H6. Okay, depending on what you have over there. Okay, so here I have, okay, O2. Yeah, O2. So there are 2 atoms of oxygen. Okay, and then, okay, normally when something is added over there, okay, so we have the C6. Okay, we know that there are 2 carbon atoms is being added. Yeah. So another indication that I have is going to be a yellow precipitate when you test with alkaline I2. So alkaline I2, when you have yellow precipitate, that compound is going to be CHI3. This one no need to worry so much. This one you should know. Yeah. So it means this compound, I know that it can contain, okay, either, okay, it can contain something that has CH3, okay, C double bond O, 1R group. It can be something like this. Or it can be also 1R group, okay, carbon OH, okay, CH3 and then H. It can be like this. Yeah. So it depends, okay, what we have over there. So if I put over there, okay, roughly, okay, I know that I have alcohol, for example. Okay, if I have alcohol, for example, I am going to have, okay, this D. Okay, so let's say here I'm assuming, yeah, I'm assuming that I have alcohol. Okay, but okay, if you react, okay, if you react with Br2 over here, they say that they are going to give you something like this. Yeah. So if I have just alcohol, let's actually try to calculate. If I have alcohol, okay, maybe I have carbon, okay, carbon, and then I will have CH3, okay, and then I have hydrogen, and then OH. Okay, so that is one of it. Okay, so I have all this, and then I still need another one more O. Yeah, another one more O. So maybe, yeah, I can calculate. Okay, let's say for example, okay, if I have C6H5. Okay, so here is a C2. Okay, and then I have H4, H5. Okay, and then O. Okay, so if I count C8, H10, O. Yeah, C8, H10, and O. So there's a lot of hydrogen already. Yeah, because I want 8 hydrogen. Yeah, so I already have 10 hydrogen if I use O. Yeah, so let's actually try to make the molecule simple without a lot of hydrogen. So the only way that I can think of, yeah, if I use the double bond O, then the hydrogen will decrease. So if let's try with the double bond O. Yeah, so I don't want this. Okay, but I still want to maintain the CH3. Okay, so double bond O. Okay, there is no hydrogen. Okay, and then, okay, I need I have 3 hydrogen here. Okay, there's no hydrogen here. So 1, 4, 5, 6, 7, 8. Okay, I have 8. Roughly okay. Yeah, roughly okay. Okay, but okay, I know that I need to have another oxygen. Yeah, so where do I put another oxygen? So I will just maybe I put the oxygen, okay, maybe here. Okay, if I put the oxygen over here, okay, that H has been replaced. Yeah, so I think better to put the H here. Okay, because now, okay, if I have 3 hydrogen, I have 4, 5, 6, 7, 8. Okay, so it matches. Okay, so roughly, okay, still not confirmed yet. Okay, roughly, we have a rough idea that it might be C double bond O CH3 and then OH over here. Okay, and then okay, let me erase this part also. So I roughly know that I have the idea that it can be like this. Yeah. But okay, when you react with Br2, normally we see when it reacts with Br2 and then Br2 came in, normally we think that it might be double bonds might be there. Yeah. But in this case, okay, you see that okay, this is going to be, if I count all this, it's going to be C, okay, just now we counted, yeah, C6H, okay, H4, and then you have COCH3, and then we have OH. If I combine them all together, C8, okay, all done, and then hydrogen 8, okay, and then I have O2, yeah, so this one is okay, yeah, this one is okay. But when I react with Br2, you see that the hydrogen suddenly becomes 6, yeah. So it means that if there is going to be decrease in number of hydrogen, most likely they are going to be attached to your benzene group. Yeah, then only the hydrogen will decrease. Like for example, C6H6. So why we get C6H4? Because they are attached directly. Yeah, but this one okay should be happening okay with okay, this is going to be with OH, okay, you do not need any halogen carriers, so it just can come in. So here, okay, but do remember the position, yeah, the position that is going to be formed, yeah. So if you have the OH, okay, OH will activate position 2, 4, 6, yeah. So here I can see only position 2 and 4 available, 6 is not available. So I will actually put the Br, okay, somewhere here, okay, let me erase this part. Okay, I will put C double bond O CH3, and then OH, I will put the Br here, I will put the Br here. So now, if you look at the first statement, it contains 6 peaks. Let's see whether they really contain 6 peaks or not, yeah? So peak number 1, this is 1, okay? So peak number 2, okay? And then this is going to be, if you put a symmetrical molecule over there, yeah? So this is peak number 3, the carbon. Number 4 is the same as this, number 4. Number 5, they are symmetrical, so this is going to be number 5, and this is going to be number 6. So we know that this is going to be the 6, okay, 6 peaks, okay, that can exist, okay. So we are in the right track. Yeah, so I'll erase this part. So roughly all this, okay, is correct. Yeah. So now, okay, when I have the reaction, okay, with the alkaline I2, okay, what will happen? Okay, this one, okay, we know that the CH3, okay, is going to become CI3, then after that CHI3, and this entire molecule, okay, the D, okay, they are going to become, okay, C double bond O OH. Okay, normally if you use excess, then it's going to be O minus and A plus, yeah, the salt. Okay, but this one is going to be changing into carboxylic acid over there. And then, okay, finally you react with PCl5. Okay, the moment you react with PCl5, you can see that, okay, this carboxylic acid is the one that normally will be replaced, okay, by the Cl. Yeah, so this one PCl5 is going to be at room temperature, so they will not react with phenol. So carboxylic acid do react with PCl5. Yeah, when they react, you can see the oxygen is going to remain as 2. Yeah, no longer 3. So you can see the oxygen is 2, and then 1 Cl went in. So E will be this one. Okay, so I'll just put, okay, C double bond O, and then this is Cl, and then I put a OH over there. This is the structure. So if you want to check, okay, it's going to be C6, okay, 2 places, so H4, COCl, and OH. Okay, let's actually check. C7, okay, and then hydrogen is 5, oxygen is 2, Cl is 1. So let's see. C7H5O2Cl. So we are in the right track, yeah. So then they are going to react, okay, with propan-2-ol. Now, propan-2-ol, do remember, phenol do not react with alcohol. Okay, they are going to react, okay, with the acyl chloride. Okay, so the acyl chloride is going to react with propan-2-ol. So propan-2-ol, I will just write down the OH like this. Okay, so this is CH3. This is CH3, so this is H. Yeah, this is propan 2-ol. Yeah, and then what will happen? The Cl, okay, from the acyl chloride, they are going to join with this H. Yeah, and they are going to form ester. Yeah, so if I draw, okay, I think the better way to represent is to represent them something like this. And then you put the OH over here. So this is OH. I'll put like this. And then bonded to C, bonded to C, bonded to O. Okay. And then this carbon is bonded to this O. So I'll put this O. And then you have C. Okay. And then you have H and then 2CH3. So maybe I'll put the H here and then CH3 and then CH3. So if you want to represent them, yeah, you want to draw like this also, okay. Or you want to show in form of a skeletal formula also, okay. Let's try skeletal formula. So this one, okay, is OH. And then I have CO. So let's say I'll go here. Or maybe just go straight C, and then maybe like this. So maybe you draw, yeah, so C, okay, C is here, double bond O, and then you have O, and then you have C, and then you have another C there. You have another C, okay, no need to show all. So this one is all done, okay. So this one, okay, is going to be connected to the benzene, yeah. So maybe I draw benzene. And then maybe the carbon is joined here, okay. So maybe I'll just draw the carbon like this, okay, join here, and then it's going to be joined to OH. I think this one is better, okay. So I will keep it this way. Or you want to still don't want to have a lot of problem in drawing and so on. You want to still give this as an answer, no problem. Okay, you can go ahead, no problem. Okay, that's it. Yeah, for question number 9, and we have done, okay, with the paper 4.1, okay, May, June. Yeah, thank you guys.